Hello there, and welcome to the Scientist Sleepy. Tonight, we embark on a gentle exploration, a calm lecture, into the very origins of our home. We will investigate the fascinating phenomena of how our solar system, this vast and wondrous arrangement of planets, moons, and stars, came to be. Prepare for a journey through time, revealing the profound and extraordinary process that sculpted the cosmic cradle in which we find ourselves. Now, if you would, allow yourself to settle in. Find a comfortable position, a position of ease. And if this exploration resonates with you, feel free to gently press that like button and perhaps consider subscribing. Subscribing ensures you won't miss our continuing journeys into the quiet wonders of the universe, a shared space for those who seek deeper understanding. And if you feel inclined, we always welcome a quiet thought or observation in the comments below. Let us now drift into the nebular dust and the stellar winds, into the very making of our solar system. The cosmic cradle, a nebulous beginning. Long before the familiar celestial dance of planets around our sun, our solar system began not with a bang, but with a whisper, a vast, ethereal cloud of gas and dust. This was the cosmic cradle, a nebula, a sprawling expanse of the raw materials of creation, stretching for light years across the interstellar void. Imagine a celestial fog, not of water vapor, but of hydrogen and helium, the lightest and most abundant elements forged in the universe's earliest moments, mingled with trace amounts of heavier elements, the ashes of long-dead stars. These heavier elements, like carbon, oxygen, silicon, and iron, were synthesized within the hearts of stars and then dispersed into space through stellar winds and supernova explosions, seeding the next generation of cosmic clouds. Our nebula was a product of this grand cosmic recycling program, a reservoir of potential, holding within it the blueprints for everything that would eventually come to be. It wasn't a uniform, placid entity, but a dynamic, turbulent place with swirling currents and varying densities, a canvas upon which gravity and other cosmic forces would soon begin to paint. The sheer scale of this nebula is almost incomprehensible. It contained perhaps hundreds of times the mass of our current solar system, a vast reservoir from which our sun and its planetary family would eventually coalesce. Within this swirling cosmic soup, the seeds of stars and planets lay dormant, awaiting the trigger that would set them into motion. The initial state of this nebula was one of near equilibrium, a delicate balance between the outward pressure of the gas and dust particles and the inward pull of gravity. However, even the slightest disturbance, a passing shockwave from a nearby supernova, or the gravitational influence of a passing star, could be enough to disrupt this fragile balance and initiate the dramatic process of collapse. This initial state, this vast, diffuse cloud, is the true genesis of our solar system, the primordial soup from which all its wonders would eventually emerge. It was a time of profound potential, a quiet, majestic prelude to the fiery birth of a star and the formation of worlds. The very fabric of space was woven with the elements that would one day form our home, a testament to the interconnectedness of all things in the cosmos. This nebular hypothesis, first proposed in the 18th century, remains our most robust explanation for the formation of planetary systems, a testament to humanity's enduring quest to understand our place in the grand cosmic tapestry. The silent, patient work of gravity within this immense cloud set the stage for one of the most magnificent events in astronomical history, the birth of our sun. Within this vast, quiescent cloud, a silent, inexorable force began to assert its dominance: gravity. It is the fundamental sculptor of the cosmos, the architect of galaxies, stars, and planets. In our nebula, gravity began to pull the scattered particles of gas and dust closer together, a process that would take millions of years and culminate in the birth of our sun and the formation of its accompanying planetary system. Imagine countless tiny specks, each with a minuscule gravitational pull, all working in concert, gradually drawing their neighbors nearer. As more and more matter congregated in certain regions, the gravitational attraction in those areas intensified, accelerating the process. This wasn't a sudden event, but a slow, patient gathering, a cosmic ballet of attraction. Think of it like a gentle, persistent tide, gradually drawing the scattered waters of the nebula towards denser pockets. These denser regions began to grow, becoming more massive and exerting a stronger gravitational influence on the surrounding material. This gravitational collapse is the driving force behind star formation. As the cloud contracted, it began to spin, a consequence of the conservation of angular momentum. Just as a figure skater spins faster when they pull their arms in, the nebula's rotation accelerated as it shrank. This spinning motion caused the cloud to flatten into a disk, much like a pizza dough being tossed and stretched. This disk, known as an accretion disk, became the birthplace of our sun and its planets. At the center of this swirling disk, the gravitational pull was strongest, drawing in the vast majority of the matter. Here, the density and pressure began to rise dramatically. The particles of gas and dust collided with increasing frequency and intensity, converting their kinetic energy into heat. This was the nascent stage of a star's ignition, a protostar beginning to glow with its own internal warmth, though not yet the brilliant furnace we know today. The surrounding disk, however, was not a uniform entity. It possessed a gradient of temperature and composition. Closer to the forming protostar, it was intensely hot, where only the most refractory materials like metals and rocky silicates could condense into solid particles. Further out, beyond what would become the asteroid belt, the temperature dropped significantly, allowing volatile compounds such as water, methane, and ammonia to freeze into ice. This temperature gradient, known as the frost line, played a crucial role in determining the types of planets that would form in different regions of the solar system. The gravitational collapse of the nebula, therefore, initiated a chain reaction of events, from the spinning and flattening of the cloud to the heating and eventual ignition of a star, all orchestrated by the fundamental force of gravity. And in that vast, swirling cradle, gravity, the silent conductor, began its patient symphony, weaving dust and gas into the very fabric of existence. The stellar nursery, where stars ignite. Imagine, if you will, vast, ethereal clouds drifting through the silent, inky blackness of interstellar space. These are not mere wisps of fog, but colossal molecular clouds, the true stellar nurseries of the cosmos. Within their immense depths, gravity, that silent sculptor of the universe, begins its patient work. These clouds are primarily composed of hydrogen and helium, the primordial elements forged in the Big Bang, laced with trace amounts of heavier elements, the ashes of long-dead stars. They are cold, incredibly cold, with temperatures often dipping to just a few degrees above absolute zero. This frigidity is crucial, for it allows the gas and dust particles to clump together. Within these colossal nebulae, there are often regions of slightly higher density, perhaps triggered by the shockwave from a nearby supernova explosion or the gravitational nudge of a passing star. These denser pockets act as seeds, drawing in more and more surrounding material. As more matter accumulates, the force of gravity intensifies, pulling everything inward with an ever-increasing embrace. This inward pull, this relentless compression, is the fundamental force that initiates the birth of a star. As the cloud collapses, it begins to spin, a consequence of the conservation of angular momentum. This spinning motion causes the cloud to flatten into a disk, much like a pizza dough being spun in the air. At the center of this collapsing, spinning disk, the pressure and temperature begin to rise dramatically. The gravitational potential energy of the infalling matter is converted into heat, a cosmic forge igniting within. This central, incandescent core is the protostar, the embryonic stage of a star. It is not yet a true star, for nuclear fusion has not yet begun, but it glows brilliantly with the heat of its own compression. The surrounding disk, the accretion disk, continues to feed the protostar, delivering more material and increasing its mass. Within this disk, not all the material will be swallowed by the nascent star. Some will coalesce, beginning the process of forming planets, asteroids, and comets. The protostar itself will continue to contract and heat up for millions of years. Its core will become denser and hotter until, at a critical point, the immense pressure and temperature will be sufficient to overcome the electrical repulsion between atomic nuclei. This is the moment of ignition. Hydrogen nuclei, the simplest of atoms, will begin to fuse together, forming helium. This nuclear fusion releases an enormous amount of energy in the form of light and heat. This outward rushing energy creates an outward pressure that finally balances the inward pull of gravity. The protostar has become a true star, stable and shining, a new beacon in the cosmic darkness. The stellar nursery, once a diffuse cloud, is now a vibrant system, with a central star radiating warmth and light, and a surrounding disk of material that will eventually blossom into a planetary system, a testament to the universe's endless capacity for creation. The processes that occur within these nebulae are not just about forming stars. They are the very genesis of the elements that make up everything we know, including ourselves. The dust that formed our planet, our sun, and even our own bodies originated in these magnificent cosmic cradles. Within the quiet expanse, gravity's gentle hand awakens sleeping gas, and a star's first radiant sigh paints the darkness with the promise of worlds to come. The sun's first breath, a protostar emerges. Imagine, if you will, a vast, dark expanse, a cosmic canvas painted with the ethereal glow of distant stars and the subtle shimmer of interstellar gas. Within this immense, silent theater, a grand drama was beginning to unfold, a story of creation that would ultimately give birth to our very own sun. This was not a sudden, explosive event, but rather a slow, patient accumulation, a gathering of cosmic dust and gas driven by the fundamental force of gravity. Our solar system, you see, didn't spring into existence fully formed. It began as a colossal cloud of gas and dust, a nebula, perhaps many light years across. These nebulae are the stellar nurseries of the universe, vast, cold, and diffuse regions where the raw materials for stars and planets lie dormant, waiting for a trigger. What could have disturbed such a placid, immense expanse? It might have been the shockwave from a nearby supernova, the explosive death of a massive star, or perhaps the gravitational nudge from a passing star. Whatever the catalyst, this disturbance initiated a subtle but profound change within the nebula. Gravity, the invisible architect of the cosmos, began to assert its influence. Regions within the cloud, slightly denser than their surroundings, started to attract more and more of the surrounding gas and dust. This process is known as gravitational collapse. As more material gathered, the gravitational pull intensified, accelerating the collapse. Picture it like a snowball rolling down a hill, gathering more snow and growing larger and faster. This collapsing region, the precursor to our sun, began to spin. As the cloud contracted, it rotated faster, a phenomenon governed by the principle of conservation of angular momentum, much like an ice skater pulling their arms in to spin more quickly. This spinning motion caused the cloud to flatten into a disk, with the densest concentration of matter at its center. It is within this swirling, collapsing heart of the nebula that our protostar, the embryonic sun, began its remarkable journey. The relentless compression of gas and dust at the center generated immense heat and pressure. Atoms began to collide with increasing vigor, their kinetic energy converted into thermal energy. The temperature rose and the density increased, creating a glowing, opaque sphere of gas. This was the protostar, a nascent star, not yet burning with the steady, radiant fire of a true sun, but radiating heat and light from the sheer energy of its own gravitational contraction. It was a cosmic ember, slowly but surely gathering strength. This protostar was a dynamic entity, constantly accreting material from the surrounding disk. Jets of gas were often ejected from its poles, a spectacular release of energy as the protostar shed excess angular momentum. These jets, though seemingly destructive, played a crucial role in shaping the nascent solar system. The protostar was a crucible, a place of intense transformation, where the raw ingredients of a star and its future planetary family were being forged under the immense power of gravity. The energy generated by this gravitational collapse was the initial source of the protostar's luminosity. It wasn't yet nuclear fusion, the process that powers mature stars, but a precursor, a glowing heat born from the very act of its formation. This initial phase of stellar birth is a testament to the slow, deliberate, and powerful forces that shape the universe. It is a reminder that even the most brilliant lights begin as quiet whispers, gathering strength over eons. The sun, our life-giving star, did not simply appear. It was patiently built, breath by cosmic breath, from the scattered remnants of a primordial nebula. The sun's first breath was a quiet gathering, a nascent glow born from the deep embrace of gravity. The accretion disk, a flattening vortex asterisk. Imagine, if you will, the remnants of that initial, vast cloud of gas and dust. As gravity began its inexorable work, pulling this material inwards, it wasn't a simple collapse into a single point. Instead, due to the conservation of angular momentum, the spinning cloud began to flatten. Think of a figure skater pulling their arms in, they spin faster. Similarly, as the nebula contracted, its rotation increased. This increased rotation created an outward centrifugal force that counteracted gravity, particularly in the plane of rotation. The result was a vast, flat, rotating disk of gas and dust, much like the spinning batter of a pancake, but on an astronomical scale. This is the accretion disk, the very birthplace of our solar system. It was a dynamic environment, a swirling crucible where the ingredients for planets were brought together. Within this disk, the density of material was highest near the center, where the nascent sun, the protostar, was already beginning to shine. The disk extended outwards, gradually thinning with distance from the central star. It wasn't a static structure, it was a constantly evolving entity. Material within the disk was in motion, spiraling inwards towards the protostar, feeding its growth, while also jostling and colliding with other particles. These collisions were not always destructive. In fact, they were the very mechanism by which larger and larger clumps of matter began to form. Tiny dust grains, no larger than a speck of flour, would stick together upon impact, forming larger pebbles. These pebbles, in turn, would collide and aggregate, growing into boulder-sized objects, then into kilometer-sized planetesimals. The accretion disk was a remarkably efficient factory for planet building, concentrating matter in specific regions, and providing the conditions for these slow, deliberate collisions and mergers. The temperature within the disk also played a critical role. Near the protostar, it was incredibly hot, vaporizing many of the more volatile elements. Further out, beyond a certain boundary we'll explore later, the temperatures dropped significantly, allowing these volatile elements to condense into solid ice. This temperature gradient was fundamental in determining the composition of the planets that would eventually form. The inner regions of the disk, being hotter, would primarily accrete rocky and metallic materials, leading to the formation of the terrestrial planets. The outer regions, cooler and richer in volatile ices, would allow for the rapid accumulation of gas and ice, forming the gas giants. The accretion disk was not a uniform entity. It possessed subtle variations in density and composition that would influence the final architecture of our solar system. It was a complex, turbulent, yet incredibly ordered structure, a testament to the fundamental laws of physics at play in the cosmos. The sheer scale of this disk is almost incomprehensible. Imagine a pancake stretching across billions of kilometers, with a young star at its very heart. This swirling disk was the stage upon which the grand drama of planetary formation would unfold, a testament to the power of gravity and the persistent dance of matter and energy. The process was slow, taking millions of years, a patient unfolding of cosmic destiny. Within this flattened vortex, the seeds of worlds were sown, each particle playing its part in the grand design. The disk provided the raw material and the necessary dynamics for the initial stages of planet formation, a crucial step in the story of our solar system. It was a period of intense activity, a cosmic construction zone where the very fabric of our planetary neighborhood was being woven. The flattened shape of the disk was not just a geometric curiosity. It dictated where and how planets would form, concentrating matter into a relatively thin plane. This plane, the ecliptic, is where we find most of the planets orbiting our sun today, a direct legacy of that early, flattened vortex. The accretion disk was a powerful engine, a source of both material and energy, driving the early evolution of our solar system. It was a place of constant collision and aggregation, a chaotic yet ultimately constructive environment. The disk was a dynamic equilibrium, a balance between the inward pull of gravity and the outward force of rotation. It was a temporary but essential phase, a necessary precursor to the formation of the stable planetary system we observe today. The subtle density waves and turbulence within the disk played a crucial role in guiding the formation and migration of planets, shaping their orbits and their eventual sizes. The accretion disk, this flattened vortex of cosmic material, was the very crucible in which the building blocks of our solar system were assembled, a grand, swirling stage set for the emergence of worlds. Within this flattened vortex, matter coalesced, a cosmic dance of dust and gas, laying the foundation for the worlds to come. The frost line, a crucial dividing zone. Imagine, if you will, a vast, swirling disk of gas and dust, the nascent solar system. Within this cosmic cauldron, the seeds of planets are beginning to coalesce. But not all locations within this disk are created equal, and a critical factor, temperature, dictates the very nature of the worlds that will eventually form. This is where the concept of the frost line, or more accurately, the snow line, becomes paramount. It's a boundary, not a physical wall, but a gradient of increasing coldness as one moves away from the intensely hot, young sun at the center. This frost line is not a fixed point. Its position evolved over time as the young sun's luminosity changed. However, in the early solar system, it was a profoundly important demarcation. Inside this invisible boundary, closer to the sun, temperatures were too high for volatile compounds, substances like water, ammonia, and methane, to freeze. They remained in a gaseous state, or perhaps as tiny liquid droplets dispersed within the nebula. This meant that the solid building blocks available for planet formation in the inner solar system were primarily rocky materials and metals. These elements are less abundant in the universe compared to the lighter gases like hydrogen and helium. Consequently, the planets that formed within the frost line, Mercury, Venus, Earth, and Mars, are relatively small, dense, and rocky. They are the terrestrial planets with solid surfaces. Now venture beyond this frost line. Here, the temperature drops significantly. This is where the magic of freezing occurs. Water could freeze into ice, ammonia into solid crystals, and methane into a solid. Suddenly, the available raw materials for planet formation expanded dramatically. Instead of just silicate dust and metals, planetesimals could now incorporate vast quantities of ice. These ices, being composed of lighter, more common elements like hydrogen, oxygen, nitrogen, and carbon, were far more abundant in the solar nebula than the heavy elements. This abundance of icy material beyond the frost line allowed for a fundamentally different type of planetary growth. The solid cores that formed here could become much larger, much faster, because they had so much more material to accrete. And once these cores reached a critical mass, perhaps around 10 times the mass of Earth, their gravity became strong enough to begin attracting and holding onto the abundant hydrogen and helium gas that still permeated the outer reaches of the solar nebula. This process, known as gas accretion, is how the gas giants Jupiter, Saturn, Uranus, and Neptune came to be. They are not merely large icy bodies. They are colossal worlds dominated by hydrogen and helium atmospheres, with much smaller rocky or icy cores deep within. The location of the frost line, therefore, played a pivotal role in determining the architecture of our solar system. It created a distinct dichotomy: the small, rocky inner planets and the massive, gaseous outer planets. It's a testament to how subtle shifts in environmental conditions, like temperature gradients in a primordial cloud, can lead to vastly different outcomes in the grand process of celestial formation. The frost line was, in essence, a cosmic recipe card, dictating the ingredients and the cooking temperature for the worlds that would eventually populate our stellar neighborhood. The chill of the frost line, a silent arbiter, divided the realm of rock from the abundance of ice, shaping the very character of the worlds we call home and those that lie in distant, frozen splendor. Rocky beginnings, inner planet formation. In the nascent solar system, a mere few million years after the initial collapse of the solar nebula, a dramatic and intricate dance began to unfold in the inner reaches, closest to the burgeoning sun. This region, characterized by its intense heat and the relentless solar wind, was a crucible for a very different kind of planetary formation than that occurring in the colder, outer realms. Here, in the shadow of our young, fiery star, the seeds of what would become the terrestrial, or rocky, planets were sown. The fundamental building blocks were not the vast quantities of ice and gas that dominated the outer system, but rather heavier elements, silicates, iron, nickel, that could withstand the sun's thermal onslaught. These elements, forged in the hearts of ancient stars and scattered across the cosmos, had coalesced into dust grains within the swirling nebula. As this nebula contracted, these dust grains began to collide. At first, these were gentle electrostatic attractions, like tiny magnets drawing each other together. But as more material accumulated, gravity began to assert its dominance. These accumulating clumps of dust, growing larger and more substantial, are known as planetesimals, ranging from pebble-sized fragments to objects tens or even hundreds of kilometers across. These planetesimals, like celestial marbles, then began their own gravitational ballet, their paths intersecting, leading to frequent and often violent collisions. In the inner solar system, these collisions were not always destructive. While some impacts would shatter smaller bodies, larger ones could lead to accretion, where the material of one planetesimal would merge with another, building up a larger, more massive object. Imagine a cosmic game of billiards, but where the balls don't just bounce off each other, they merge and grow. The intense heat of the inner solar system played a crucial role in shaping these nascent worlds. Volatile elements such as water, methane, and ammonia would have vaporized and been pushed outwards by the solar wind, leaving behind the refractory or heat-resistant materials. This is why the inner planets Mercury, Venus, Earth, and Mars are predominantly rocky, with solid surfaces composed of silicate rocks and metallic cores. The process was not a smooth, linear progression. It was a chaotic, dynamic period, marked by constant bombardment and gravitational tug-of-war. The relative abundance of these heavier elements in the inner solar nebula was also critical. While the nebula as a whole was composed primarily of hydrogen and helium, the heavier elements, though a smaller fraction, were concentrated enough in the inner regions to form these substantial rocky cores. These growing cores acted as gravitational anchors, attracting more planetesimals and accelerating their own growth. The more massive a core became, the stronger its gravitational pull, and the more material it could gather. This feedback loop was essential for the formation of planets, rather than just a collection of scattered asteroids. Over tens to hundreds of millions of years, these countless collisions and mergers gradually sculpted larger and larger bodies. The largest of these growing objects would eventually sweep up most of the available material in their orbital paths, clearing their vicinities and becoming the planets we recognize today. The differences we see between the inner planets are a testament to the subtle variations in their formation environments and the subsequent events they endured. Some may have grown larger and more massive, retaining a greater degree of internal heat and geological activity. Others might have experienced more significant impacts that shaped their size, composition, or even their rotational characteristics. The very process of accreting material meant that the inner planets inherited a rich tapestry of elements, providing the raw materials for complex geology, and in the case of Earth, the very foundations of life. The rocky beginnings of our inner solar system were a testament to the power of gravity, the resilience of certain elements, and the raw, energetic forces at play in the early universe, a process of violent creation that ultimately laid the groundwork for our own existence. And so, the solid ground beneath our feet began as cosmic dust, drawn together by gravity's persistent embrace, a testament to the universe's ability to build worlds from the remnants of stars. Gaseous giants, outer planet accretion. Beyond the frost line, where the icy depths of space held sway, a different kind of planetary genesis unfolded. Here, the building blocks were not merely dust grains and rocky fragments, but vast quantities of frozen volatiles, water ice, methane ice, ammonia ice, abundant and readily available. This abundance was the key, the fundamental difference that allowed for the spectacular formation of the gas giants. Imagine, if you will, a colossal, invisible snowball continuously growing. This is the essence of outer planet accretion. The process was driven by gravity, but on a scale far grander than that seen in the inner solar system. Initially, these nascent giants, or cores, grew by accreting these icy materials, much like their rocky inner siblings, but with a much richer supply. These cores rapidly reached a critical mass, perhaps around 10 times the mass of Earth. This threshold was crucial, because at this point, their gravitational pull became so immense that they could begin to directly capture and hold onto the vast reservoirs of hydrogen and helium gas that permeated the primordial solar nebula. This was not a gentle process. It was a ravenous consumption of the surrounding gas. As these cores grew, their gravity intensified, allowing them to sweep up more and more of the nebular gas. This led to a runaway effect, where the more gas they captured, the stronger their gravity became, and the more gas they could capture. It was a self-perpetuating cycle of immense growth. The hydrogen and helium, being the most abundant elements in the universe, were readily available to fuel this insatiable appetite. Unlike the rocky planets, which were limited by the availability of silicates and metals. The gas giants were limited only by the amount of gas they could gravitationally bind before the solar nebula dissipated. This led to their enormous sizes and their distinctive compositions, dominated by hydrogen and helium, mirroring the composition of the Sun itself. The inner planets, by contrast, formed from heavier elements that could withstand the Sun's heat, while the gas giants formed in the colder outer regions where ices could condense, and their gravity was strong enough to hold onto the lighter gases. The process was not uniform. There were differences in the timing and the amount of gas available that contributed to the distinct characteristics of Jupiter, Saturn, Uranus, and Neptune. Jupiter, being the most massive and forming earliest, captured the most gas, becoming the largest planet. Saturn, forming slightly later and with a slightly less dense gas environment, also grew to immense proportions, though not quite as large as Jupiter. Uranus and Neptune, forming even later and in regions with less gas, were smaller and are often referred to as ice giants, because their cores likely contained a larger proportion of ices relative to gas, and their hydrogen-helium envelopes were less substantial. The accretion process was a race against time. The solar nebula was not a static entity. It was a dynamic environment, gradually thinning and dissipating as the young sun's stellar winds began to blow. The gas giants had to grow large enough to capture and retain their atmospheres before this gas was blown away. This race against dissipation is a key reason why there are only a few gas giants and not a vast number of them. The sheer scale of this gravitational capture is difficult to comprehend. Imagine an object so massive that it could pull in and hold onto an atmosphere equivalent to hundreds of Earths. This process shaped the architecture of our solar system, creating the distinct zones of rocky inner worlds and gaseous outer giants. It was a grand cosmic ballet of gravity and abundant matter, orchestrated by the immense forces of star formation. The sheer volume of gas involved in the formation of these colossal worlds is a testament to the raw power of gravity and the vastness of the early solar nebula. These planets are not solid spheres in the way Earth is. They are primarily spheres of gas and liquid, with perhaps a small rocky or icy core at their center. The immense pressure within these giants compresses the hydrogen and helium to such an extent that it behaves in exotic states, like liquid metallic hydrogen in Jupiter and Saturn, which generates their powerful magnetic fields. The formation of the gas giants was a defining moment in the history of our solar system, setting the stage for the diverse planetary landscape we observe today. It was a process of immense scale, driven by the fundamental forces of the universe, and it resulted in some of the most awe-inspiring celestial bodies in our cosmic neighborhood. The vastness of their atmospheres, a direct consequence of this rapid accretion, speaks to the sheer quantity of hydrogen and helium available in the early solar nebula. The process was so efficient that these planets essentially became miniature versions of the Sun in terms of their elemental composition, though vastly smaller in mass and lacking the critical mass for nuclear fusion. The unique characteristics of each gas giant, their sizes, their atmospheric compositions, their ring systems, are all subtle variations on this fundamental theme of gas accretion, influenced by their orbital positions, the timing of their formation, and the specific conditions within the swirling nebula. In the cold expanse, a monumental hunger for gas birthed giants, their gravity a cosmic embrace that shaped the very architecture of our celestial home. The Grand Tack, Jupiter's mysterious migration. Our solar system, as we know it, is a product of immense cosmic forces and a long, dynamic history. While we often perceive the planets in their current orbits as fixed and eternal, The reality is that their positions have shifted dramatically over billions of years. Among the most profound and influential of these shifts is the story of Jupiter's migration, a phenomenon known as the grand tack. Imagine, if you will, a gravitational dance of colossal proportions, where the largest planet in our solar system, Jupiter, didn't simply form in its current location, but embarked on a remarkable journey inward towards the Sun, only to reverse course and migrate outward again. This seemingly small alteration in its path had monumental consequences for the formation and architecture of the entire solar system, particularly for the inner terrestrial planets like our own Earth. The prevailing theory suggests that as Jupiter formed from the swirling disk of gas and dust surrounding our young Sun, its immense gravitational pull influenced the surrounding material. Initially, it is believed that Jupiter migrated inward, perhaps as far as the orbit of Mars, or even closer. This inward journey would have been a period of intense gravitational interaction, shaping the orbits of smaller planetesimals and potentially scattering them. It's a mind-boggling thought to consider the largest planet in our solar system, traversing the very regions where the rocky planets would eventually coalesce. The implications of this inward migration are far-reaching. For instance, it's hypothesized that Jupiter's presence in the inner solar system could have prevented the formation of a fully fledged planet in the asteroid belt, leaving behind the fragmented remnants we observe today. Furthermore, its gravitational influence might have cleared out much of the material that could have otherwise contributed to the growth of inner planets, or conversely, delivered specific types of material. However, the story doesn't end with Jupiter settling in the inner solar system. The grand tack hypothesis posits that Jupiter's inward migration was eventually halted and reversed by the gravitational influence of another giant planet, Saturn. As Saturn formed and moved into proximity with Jupiter, their mutual gravitational tug-of-war created a complex orbital dynamic. This interaction, it is theorized, caused Jupiter to halt its inward journey and begin to migrate outward, back towards its current position. This outward migration would have had its own set of profound effects. As Jupiter moved away, it would have cleared out a path, potentially allowing some of the inner planets to grow larger. It also would have pushed material outward, contributing to the formation of the asteroid belt and potentially influencing the outer solar system as well. The grand tack is more than just a fascinating astronomical hypothesis. It's a crucial piece of the puzzle in understanding why our solar system looks the way it does. It helps explain the relatively small size of Mars, the composition of the asteroid belt, and the very existence and characteristics of Earth. Without this colossal migration, the conditions that allowed for the formation of life on our planet might never have arisen. The precise details of this migration are still being investigated, with ongoing research refining our understanding of the timing, extent, and precise gravitational interactions involved. But the core concept remains. Jupiter, our solar system's gravitational anchor, was once a cosmic wanderer, its path shaped by the very forces that birthed our celestial neighborhood. The grand tack of Jupiter, a cosmic waltz of immense scale, reminds us that even the most seemingly stable celestial arrangements are born from dynamic, shifting histories, a profound echo of our own transient journey through the universe. The asteroid belt, unformed worlds. Between the orbits of Mars and Jupiter lies a vast, scattered collection of rocky and metallic bodies, a region we call the asteroid belt. It is a place often depicted as a dense, perilous minefield of tumbling rocks, a dramatic obstacle for any intrepid spacecraft. However, the reality is far more subtle, and in its own quiet way, profoundly significant. The space within the asteroid belt is remarkably empty. The average distance between any two large asteroids is millions of kilometers, making a collision an exceedingly rare event. Instead of a cosmic traffic jam, imagine a sprawling, sparsely populated metropolis of celestial debris. These asteroids are not merely random fragments. They are, in essence, the unformed worlds of our solar system. During the chaotic early days of planetary formation, the immense gravitational influence of Jupiter, the king of our planets, acted as a powerful shepherd, and at times, a disruptive force. Jupiter's gravity prevented the material in this region from coalescing into a single, large planet. It stirred and tugged at the nascent planetesimals, scattering them, breaking apart larger bodies, and ensuring that a planet would never truly form in this zone. The asteroids we see today are the leftover building blocks, the cosmic detritus that never quite assembled into a cohesive whole. They are a testament to the powerful forces that shaped our solar system, a frozen moment in time, preserving clues about the conditions and materials present during its infancy. Each asteroid, from the largest, like Ceres, which is now classified as a dwarf planet, to the smallest pebble, offers a unique window into the past. They are composed of a variety of materials, reflecting the different temperature gradients and chemical compositions that existed in the early solar nebula. Some are stony, others are metallic, and some are a mixture, often containing significant amounts of carbon. Studying their composition, their orbits, and their relationships to one another allows scientists to piece together the complex puzzle of solar system formation. We can learn about the distribution of elements, the intensity of early solar radiation, and the frequency of collisions that occurred billions of years ago. The asteroid belt, therefore, is not a void, but a treasure trove of scientific data, a library of ancient history written in rock and metal. It represents a path not taken, a planetary genesis interrupted, leaving behind a diverse collection of objects that continue to intrigue and inform us about our cosmic origins. It's a stark reminder that sometimes the most profound insights come not from grand, completed creations, but from the very fragments that failed to coalesce, offering a unique perspective on the delicate balance of cosmic forces. In the silent, vast expanse, the asteroid belt whispers tales of what might have been, a celestial graveyard of planets yet to be born, reminding us that even in incompleteness, there is profound cosmic wonder. The Kuiper Belt, icy remnants of creation. Beyond the orbit of Neptune, far from the sun's warming gaze, lies a vast, disc-shaped region known as the Kuiper Belt. This is not an empty void, but a cosmic refrigerator, a celestial larder filled with the frozen leftovers from the solar system's birth. Imagine a vast, dark expanse, stretching from about 30 astronomical units AU, the distance of Neptune from the Sun, out to perhaps 50 AU, though its true extent is still a subject of active research. Within this immense volume, billions, perhaps trillions, of icy bodies drift. These are the primordial building blocks that never quite coalesced into full-fledged planets, a testament to the chaotic and dynamic nature of our early solar system. The objects within the Kuiper Belt, often referred to as Kuiper Belt objects, KBOs, or trans-Neptunian objects, TNOs, are composed primarily of frozen volatile compounds such as methane, ammonia, and water ice, mixed with rock and dust. Their frigid temperatures, only a few degrees above absolute zero, have preserved them in a state remarkably similar to their composition billions of years ago. This makes them invaluable scientific archives, offering a direct window into the conditions and materials present during the formation of our Sun and planets. The Kuiper Belt is not a uniform, densely packed region. Instead, it's thought to be sparsely populated, with vast distances separating individual objects. However, its sheer size means that even a sparse distribution results in an enormous number of bodies. These range in size from small, kilometer-sized chunks of ice and rock to dwarf planets, some of which are substantial enough to have achieved hydrostatic equilibrium, meaning their gravity has pulled them into a roughly spherical shape. Pluto, once considered the ninth planet, is perhaps the most famous resident of the Kuiper Belt, now classified as a dwarf planet. Other notable dwarf planets in this region include Eris, Makemake, and Haumea. The formation of the Kuiper Belt is intimately linked to the migration of the giant planets, particularly Neptune. Early in the solar system's history, the gas giants are believed to have undergone significant orbital shifts. Neptune, in particular, likely migrated outwards, scattering smaller icy bodies that formed closer to the Sun. Some of these scattered objects were flung out into the distant Kuiper Belt, while others were sent on hyperbolic trajectories, becoming the comets that occasionally visit the inner solar system. The discovery of the Kuiper Belt was a gradual process, building upon theoretical predictions. In the 1950s, astronomers Gerald Kuiper and Jan Uit independently hypothesized the existence of a belt of icy bodies beyond Neptune. Kuiper suggested a relatively flat disk, while Uit proposed a more spherical, much more distant cloud of comets. The first KBO, now known as 1992 QB1, was discovered in 1992, confirming Kuiper's hypothesis and marking the beginning of a new era in our understanding of the solar system's outer reaches. Since then, thousands of KBOs have been identified, and our understanding of this region continues to expand with each new observation. The Kuiper Belt is not static. Gravitational interactions between KBOs and occasional close encounters with Neptune can alter their orbits. Some KBOs are in stable, resonant orbits with Neptune, meaning their orbital periods are simple ratios of Neptune's orbital period. Others have more eccentric and inclined orbits, suggesting they have experienced more significant gravitational perturbations. These dynamics are crucial for understanding the long-term evolution of the solar system and the potential delivery of icy material to the inner planets, including Earth. The study of Kuiper Belt objects is vital for several reasons. Firstly, they are pristine samples of the early solar system, providing clues about the composition of the protoplanetary disk from which our solar system formed. Secondly, they are the source of short-period comets, which can pose a potential impact hazard to Earth. Understanding their distribution and dynamics helps us to assess and mitigate such risks. Thirdly, the Kuiper Belt is a frontier for exploration, with ongoing missions and planned future endeavors aiming to directly study these distant, icy worlds. The existence of the Kuiper Belt reminds us that our solar system is far more extensive and complex than what we see with the naked eye or even through early telescopic observations. It is a vast and ancient reservoir, holding secrets from the dawn of time, a silent testament to the grand cosmic ballet that shaped our celestial home. And so, in the quiet expanse beyond Neptune, the icy remnants of creation drift, a frozen library of our solar system's birth, whispering tales of the cosmos in their silent dance. The Uit cloud, our solar system's distant frontier. Imagine, if you will, a vast, invisible sphere, a cosmic bubble so immense that its outermost reaches are barely tethered to our sun. This is the Uit cloud, a theoretical reservoir of icy bodies, the most distant and mysterious frontier of our solar system. It's not a neatly defined ring like Saturn S, nor a flattened disk like the planets. Instead, it's a colossal, spherical shell, extending perhaps a quarter of the way to the nearest star. Its inner edge is thought to begin somewhere beyond the Kuiper Belt, perhaps around 2,000 to 5,000 astronomical units, AU, from the Sun, and its outer edge could stretch as far as 50,000 to 200,000 AU, or even more. To put that into perspective, Neptune, the farthest planet, orbits at about 30 AU. Pluto, in its distant orbit, reaches about 50 AU. The Oort cloud, therefore, is a region of space so vast that light itself takes months, even years, to cross it from one side to the other. What exactly populates this immense, frigid realm? The prevailing theory suggests it's a vast collection of comets, or more accurately, comet nuclei. These are primordial building blocks of our solar system, remnants from the era when the planets themselves were coalescing from the solar nebula. They are composed primarily of ice, water ice, methane ice, ammonia ice, mixed with dust and rocky material. These are the frozen ghosts of the early solar system, preserved in the extreme cold of its outer reaches. They are thought to number in the trillions, though they are spread so thinly across such an enormous volume that the average distance between any two of these icy bodies is likely to be millions of kilometers. They are, in essence, the solar system's dormant seed bank, waiting for a nudge. The existence of the Oort cloud is, for now, an inference, a brilliant piece of scientific deduction rather than direct observation. We cannot see it with our telescopes in the way we can see planets or even distant galaxies. Its existence is inferred from the orbits of long-period comets. These comets, those that take thousands or even millions of years to complete a single orbit around the Sun, originate from directions that are distributed randomly across the sky. This random distribution strongly suggests that they are being perturbed from a vast, spherical shell surrounding the Sun, rather than from a flattened disk like the Kuiper belt. The Oort cloud is a dynamic place, despite its extreme remoteness and apparent stillness. While the Sun's gravitational pull is weakest here, it's not entirely absent. More importantly, the gravitational influence of passing stars, or even the occasional encounter with interstellar gas clouds, can perturb the orbits of these icy bodies. When one of these comets is nudged, its orbit can be altered, sending it careening towards the inner solar system. If its trajectory brings it close enough to the Sun, the heat will cause its ices to sublimate, releasing gas and dust, creating the spectacular coma and tail that we recognize as a comet. These are the visitors from the Oort cloud, brief, fleeting messengers from the very edge of our cosmic home, reminding us of the solar system's ancient past. The Oort cloud represents the ultimate repository of material that was never incorporated into the planets. During the formation of the solar system, the gravitational interactions between the giant planets, particularly Jupiter and Saturn, would have flung many of these icy planetesimals outwards, scattering them into these vast, distant orbits. It's a testament to the chaotic and dynamic processes that shaped our planetary system in its infancy. It's also a potential treasure trove of information about the conditions of the early solar system, offering pristine samples of the material from which everything else was formed. Studying these comets, when they venture inwards, is like peering back in time, gaining glimpses into the chemical and physical makeup of the nebula that gave birth to our Sun and planets billions of years ago. The sheer scale of the Oort cloud is almost incomprehensible. If our Sun were the size of a grapefruit, the Oort cloud could extend for several kilometers. It is a region of profound cold, where temperatures hover just a few Kelvin above absolute zero. It is a silent, dark, and seemingly empty expanse, yet it teems with trillions of icy worlds, each a potential harbinger of a celestial spectacle. It serves as a constant reminder that our familiar planetary neighborhood is merely a small inner core within a much grander, more expansive structure. The Oort cloud, though unseen, is a vital component of our solar system's architecture. It's the source of most of the comets that grace our skies, the icy wanderers that offer fleeting glimpses into the deep past. It is the farthest whisper of our sun's gravitational embrace, a vast, spherical halo of primordial ice, holding within it the frozen secrets of our solar system's birth, a silent, distant frontier in the grand cosmic tapestry. Planetesimals, the building blocks of planets. Imagine, if you will, the early solar system, a vast, swirling disk of gas and dust, not yet organized into the familiar planets and stars we observe today. This cosmic soup, born from the remnants of ancient supernovae, was a dynamic and chaotic place. Within this immense nebula, gravity, that silent architect of the cosmos, began its intricate work. It wasn't a sudden, grand assembly, but rather a gradual, almost imperceptible knitting together of matter. Tiny particles, mere specks of dust, began to collide. These weren't violent, destructive impacts, but rather gentle, sticky collisions, aided by electrostatic forces, much like dust bunnies forming under a bed. As these initial aggregations grew, their gravitational pull, though still minuscule, increased. They began to attract more dust, more gas, and other small clumps. These growing bodies, ranging in size from a few meters to hundreds of kilometers across, are what we scientifically term planetesimals. They are the fundamental building blocks, the cosmic bricks and mortar from which planets would eventually be constructed. Think of them as the protoplanets, the intermediate stages in the grand process of planetary formation. In the inner regions of the solar nebula, closer to the nascent sun, temperatures were too high for volatile compounds like water, methane, and ammonia to condense into solid ice. Here, planetesimals were primarily composed of rocky materials and metals, silicates, iron, and nickel. These were the materials that could withstand the sun's intense heat. As these rocky planetesimals collided and merged, they grew larger, their gravitational field strengthening. This gravitational influence allowed them to sweep up more of the surrounding dust and gas, accelerating their growth. The process was a continuous cycle of accretion, where smaller bodies were incorporated into larger ones. Further out, beyond what we call the frost line, temperatures dropped significantly. This allowed volatile compounds to freeze, forming icy planetesimals. These icy bodies were much more abundant than their rocky counterparts in the inner solar system. Their sheer numbers and the lower density of the material meant that they could grow much larger, much faster. This is a crucial distinction, as it explains why the outer planets are predominantly gas and ice giants, while the inner planets are rocky and metallic. The material available in each region dictated the composition of the planetesimals that formed there. The formation of planetesimals was not a uniform event. There were likely regions where material was denser, leading to more rapid growth and the formation of larger planetesimals. These larger bodies would then dominate their orbital zones, gravitationally influencing and often accreting smaller planetesimals. This process of hierarchical growth, where smaller objects merge to form larger ones, is a cornerstone of planetary formation theories. It's a slow, patient process, unfolding over millions of years. The early solar system was a cosmic construction site, and planetesimals were the essential components. They were the seeds of planets, the raw material that gravity and time would sculpt into the diverse worlds we see today. Their existence is a testament to the power of gradual aggregation, the ability of tiny particles, given enough time and the right conditions, to coalesce into something vast and significant. These were not yet planets, but they held within them the potential for planetary existence. They were the silent, growing foundations upon which the grand architecture of our solar system would be built. Their journey from dust to planetary precursor is a fundamental chapter in the story of our cosmic origins, a story of patient accumulation and the inevitable pull of gravity shaping the very fabric of our celestial neighborhood. The collisions and mergers of these planetesimals were the gentle nudges that set the stage for the formation of Earth, Mars, Jupiter, and all the other celestial bodies that populate our cosmic home. The quiet accumulation of these cosmic fragments whispers of the patient hand of gravity, shaping worlds from mere dust. The Great Bombardment, early planetary chaos. Imagine, if you will, the nascent solar system, a swirling disk of gas and dust, still very much in its adolescence. The planets, though beginning to take shape, were far from the serene celestial bodies we observe today. Instead, they were in a period of intense, almost violent formation, a time often referred to by astronomers as the late heavy bombardment, or more broadly, the early chaotic accretion phase. This wasn't a single, brief event, but rather a prolonged era, lasting hundreds of millions of years, during which the inner planets, and indeed the entire solar system, experienced a relentless barrage of impacts. These weren't gentle nudges. These were cataclysmic collisions with planetesimals, the leftover building blocks of planetary formation and even larger protoplanets. Think of it like a cosmic construction site, where the materials are still flying around with tremendous energy. The gravity of the newly formed planets, especially the gas giants like Jupiter, played a crucial role in this chaos. Jupiter, in particular, with its immense gravitational pull, acted like a cosmic vacuum cleaner and a powerful gravitational slingshot. It tidied up much of the debris in its vicinity, but it also perturbed the orbits of many smaller bodies, sending them careening inwards towards the terrestrial planets. This gravitational stirring meant that the inner solar system was a much more dangerous place than it is now. The surfaces of the Moon, Mercury, and even the early Earth and Venus bear the indelible scars of this tumultuous period. The craters we see today, from the tiniest pockmarks to vast basins, are primarily the legacy of these early, colossal impacts. These weren't just cosmetic blemishes, they fundamentally reshaped the planets. Impacts of sufficient magnitude could have melted the crusts of these worlds, even vaporizing portions of them. They delivered volatile substances, like water and organic molecules, to the surfaces of planets that might otherwise have been dry and barren. Consider the Moon. Its heavily cratered surface is a testament to this era. Large impacts created the vast, dark mare, which are actually the solidified lava flows from magma that erupted after massive impacts breached the lunar crust. Mercury, with its relatively thin atmosphere and lack of geological activity to erase the evidence, is also a heavily cratered world, showcasing the sheer intensity of this bombardment. Even Earth, with its active geology, plate tectonics, and atmosphere, has evidence of this period, though much of the direct evidence has been erased over billions of years. The impact craters that remain, and the geological records that suggest widespread melting events, point to a world that was, at times, utterly transformed by these celestial collisions. The late heavy bombardment wasn't just about destruction. It was a critical part of the planet-forming process. These impacts contributed to the growth of planets, delivered essential ingredients for life, and shaped the very geological and atmospheric evolution of worlds. It was a period of immense energy release, a violent crucible in which the familiar planets of our solar system were forged. The sheer scale of these events is difficult to comprehend. Imagine a world being repeatedly struck by objects kilometers, even hundreds of kilometers, in diameter. The energy released by such impacts would have been staggering, capable of reshaping entire continents in an instant. The precise timing and intensity of this bombardment are still subjects of ongoing scientific debate. Some theories suggest a more gradual accretion process, while others favor a more concentrated period of intense impacts, possibly triggered by a sudden migration of the giant planets. Regardless of the exact details, the evidence is clear. The early solar system was a far more chaotic and violent place than it is today. This chaotic phase was essential for the development of the planets we know, a period of cosmic upheaval that ultimately led to a more stable, and in some cases, life-supporting, environment. The very existence of planets with their diverse characteristics owes a significant debt to this era of intense planetary chaos. It was a necessary, albeit dramatic, step in the grand cosmic ballet of creation. The forces at play were immense, shaping not just the surfaces, but the very internal structures and evolutionary paths of the planets. And so, the early solar system, a swirling, chaotic ballet of colliding bodies, gradually settled into a more ordered state, leaving behind a landscape etched with the memory of its violent birth. The formation of Earth, a fiery genesis. Imagine a time, billions of years ago, when our solar system was a chaotic ballet of dust and gas, a swirling disk of nascent matter coalescing around a young, vibrant sun. Within this cosmic crucible, the Earth we know today began its extraordinary journey. It wasn't born as the serene, life-sustaining planet we recognize, but rather as a molten, fiery sphere, a testament to the intense energies involved in planetary formation. This fiery genesis was a critical phase, shaping the very foundation of our world and setting the stage for everything that would follow. The process began with the accretion of planetesimals, small, rocky bodies that gravitationally attracted one another. As these fragments collided, their kinetic energy was converted into heat, and the growing proto-Earth began to melt. This wasn't a gentle warming, it was a global inferno. The early Earth was a sea of magma, its surface a constantly shifting landscape of molten rock. The immense gravitational forces at play, coupled with the continuous bombardment from still-forming celestial bodies, ensured that no solid crust could form for a considerable period. This intense heat was not just a surface phenomenon. It permeated the entire protoplanet, driving powerful convection currents within its molten interior. These currents were the embryonic stirrings of geological activity that would, over eons, sculpt continents and oceans. As the Earth grew larger, its gravitational pull increased, enabling it to capture more material from the surrounding protoplanetary disk. This constant influx of matter, often rich in volatile compounds like water and gases, further fueled the planet's internal heat through radioactive decay and the energy released during impacts. The very elements that would eventually form our atmosphere and oceans were being incorporated into this molten mass. The differentiation of Earth's interior began during this fiery phase. Heavier elements, primarily iron and nickel, began to sink towards the center, forming the planet's core, while lighter silicate materials floated upwards, creating the early mantle and crust. This segregation of materials was a crucial step, establishing the layered structure that defines our planet today and giving rise to its magnetic field, a vital shield against the harsh solar wind. The intense heat also played a significant role in outgassing, the process by which volatile substances trapped within the Earth's interior were released into the nascent atmosphere. Water vapor, carbon dioxide, methane, and other gases were expelled from the molten rock, forming a thick, steamy atmosphere. This early atmosphere was vastly different from our own, likely toxic to life as we know it, and incapable of retaining heat efficiently. However, it was the precursor to the atmosphere that would eventually support life. The constant bombardment, while destructive, also delivered essential building blocks, including water, which would later play a pivotal role in cooling the planet and enabling the formation of oceans. The Earth's fiery genesis was a period of immense upheaval, a violent birth that laid the groundwork for the planet's future evolution, a process of immense power and profound transformation. In this inferno, the seeds of our world were sown, a testament to the violent beauty that births existence. The moon's violent birth, a giant impact. Imagine, if you will, the early Earth, a mere few tens of millions of years old, still a molten, chaotic world, still very much in its formative stages. The cosmic ballet that brought our solar system into being was a tumultuous affair, a period of intense bombardment and gravitational wrangling. It was within this fiery crucible that the most accepted, and indeed most compelling, theory for the formation of our moon was born, the giant impact hypothesis. This isn't a gentle, gradual accretion like we might see in other planetary formation scenarios. This is a story of colossal violence, a cosmic collision on an unimaginable scale. The hypothesis suggests that early in Earth's history, a Mars-sized protoplanet, often referred to as Theia, slammed into our nascent planet. This wasn't a glancing blow. It was a direct, cataclysmic impact. The sheer energy released by such an event would have been staggering, vaporizing vast portions of both Theia and the Earth's mantle. The impact would have sent a tremendous amount of molten rock and debris hurtling into orbit around the Earth. This debris, a swirling, incandescent cloud of vaporized rock and molten droplets, would have coalesced over time, drawn together by gravity to form the moon. Think about the immense forces at play. Theia's mass is estimated to have been significant, perhaps around 10% of Earth's mass. The impact would have tilted Earth's axis and spun it at a much faster rate than it rotates today. The debris disk formed from this impact would have been incredibly hot, a swirling inferno of vaporized silicates and metals. As this disk cooled, the heavier elements, like iron, would have preferentially sunk to the center, forming the Earth's core, while the lighter silicate materials would have been ejected into orbit. This is one of the key pieces of evidence supporting the giant impact hypothesis. The moon has a much smaller iron core than Earth, and its overall density is lower. Furthermore, the isotopic composition of lunar rocks brought back by the Apollo missions is remarkably similar to that of Earth's rocks. This suggests that the material that formed the moon was largely derived from Earth itself, or at least from a body with a very similar chemical makeup. If the moon had formed independently elsewhere and been captured by Earth's gravity, its isotopic signature would likely be quite different. The sheer scale of the impact also explains why the moon is relatively large compared to its parent planet, a ratio that is unusual in our solar system. The process of accretion from this debris disk would have taken time, perhaps thousands or even millions of years, but it would have been a rapid formation in geological terms. Initially, the moon would have been much closer to Earth, possibly orbiting within the Roche limit, where tidal forces would have pulled it apart if it got too close. However, as the Earth-Moon system settled, the moon gradually receded to its current distance, a process that continues even today, albeit at a much slower rate. The energy of the impact would have been dissipated, and the molten debris would have cooled and solidified, eventually forming the solid, rocky body we see in our night sky. This violent birth explains many of the moon's characteristics, its composition, its size, and its orbit. It's a testament to the chaotic, yet ultimately creative, forces that shaped our cosmic neighborhood. It's a reminder that even the most serene celestial bodies can have origins steeped in cataclysm. And so, the moon, a silent witness to our planet's history, was forged in a fiery embrace, a celestial child born from the violent union of worlds. The Martian enigma, a world that could have been. Our journey through the formation of our solar system brings us to a world that whispers of what might have been, a place of profound scientific inquiry. Mars. The Martian enigma lies not just in its present-day arid landscape, but in the compelling evidence suggesting it was once a very different planet, a world that perhaps held the potential for life, or even a more complex existence. Imagine for a moment a young Mars bathed in the warmth of a younger sun, its surface etched with the unmistakable signatures of liquid water. Vast oceans, flowing rivers, and perhaps even rain, painting a picture starkly contrasting with the rust-colored desert we see today. Geological formations, such as ancient riverbeds, deltas, and shorelines, are not mere curiosities. They are the fossilized memories of a wetter, more dynamic epoch. These features, observed through orbital imagery and the intrepid explorations of rovers like Curiosity and Perseverance, speak of a time when Mars possessed a thicker atmosphere, capable of sustaining liquid water on its surface for extended periods. This thicker atmosphere would have provided crucial protection from the sun's harmful radiation and helped to regulate the planet's temperature, creating conditions far more conducive to the emergence and sustenance of life as we understand it. The question then arises, what led to this dramatic transformation? The prevailing scientific hypothesis points to a significant loss of Mars's atmosphere over billions of years. Unlike Earth, which boasts a strong global magnetic field generated by its molten iron core, Mars lost its protective magnetosphere early in its history. This magnetic field acts like a shield, deflecting the charged particles of the solar wind. Without this shield, the solar wind relentlessly stripped away Mars's atmosphere, molecule by molecule. As the atmosphere thinned, the atmospheric pressure dropped, causing the liquid water on the surface to either freeze or sublimate directly into vapor, vanishing into space. This process, known as atmospheric stripping, is a fundamental aspect of planetary evolution. But on Mars, it appears to have been particularly severe, leading to the desiccation of a once potentially habitable world. Furthermore, the planet's smaller size played a crucial role. Mars has only about 10% of Earth's mass. This smaller mass means it has a weaker gravitational pull, making it more difficult to retain a substantial atmosphere, especially once its internal dynamo, responsible for generating the magnetic field, ceased. The loss of internal heat, a natural consequence of a smaller planetary body, led to the solidification of its core, thus ending the generation of the global magnetic field. This loss of magnetic protection, coupled with weaker gravity, created a double whammy, accelerating the atmospheric erosion. The implications of this Martian enigma are profound. It offers a stark reminder of the delicate balance required for a planet to maintain conditions favorable for life. It fuels our scientific curiosity, driving the search for evidence of past or even present microbial life beneath the Martian surface, where it might be shielded from the harsh radiation and extreme temperatures. The ongoing missions to Mars are not just about exploring another planet. They are about understanding the fundamental processes that shape planetary habitability, and by extension, our own place in the cosmos. The possibility that life could have arisen on Mars, only to be extinguished by geological and atmospheric shifts, is a humbling and thought-provoking prospect. It underscores the preciousness of our own planet and the complex, long-term processes that have allowed life to flourish here. The Red Planet, with its silent canyons and dusty plains, stands as a cosmic testament to the ephemeral nature of habitability, a world that once might have been a blue marble, now a stark reminder of planetary change. And so, the whispers of ancient oceans on Mars, remind us that even seemingly solid worlds are in constant, magnificent flux. Venus's fiery embrace, a greenhouse catastrophe. Our journey through the formation of our solar system brings us to a planet that, in many ways, mirrors our own Earth, Venus. Yet, it is a stark reminder of how finely tuned the conditions for life can be, and how a runaway process can transform a potentially habitable world into an inferno. Venus, the second planet from our Sun, is often called Earth's sister planet due to its similar size, mass, and composition. However, beneath its thick, swirling clouds of sulfuric acid lies a surface of unimaginable heat, a testament to a catastrophic greenhouse effect that has rendered it utterly inhospitable. The story of Venus's transformation is a vital chapter in understanding planetary evolution and the delicate balance of atmospheric processes. In its early history, Venus likely possessed a substantial amount of water, perhaps even oceans, much like early Earth. The amount of solar radiation reaching Venus is about twice that received by Earth, meaning its surface temperature would naturally be warmer. However, it is believed that Venus once had a more temperate climate, capable of supporting liquid water. The crucial difference lies in its atmosphere and how it responded to the increasing solar output over billions of years. As the sun grew brighter, the planet's surface temperature began to rise, leading to increased evaporation of its water. Water vapor, as we know, is a potent greenhouse gas. This means it traps heat, further increasing the planet's temperature. This created a feedback loop. Warmer temperatures meant more evaporation, which meant more water vapor in the atmosphere, which trapped even more heat, leading to even warmer temperatures. This runaway process is known as a runaway greenhouse effect. Unlike Earth, which has mechanisms to regulate its atmospheric composition, such as the carbon cycle and the presence of life that utilizes carbon dioxide, Venus lacked these crucial checks and balances. Over vast stretches of time, this relentless heating caused all of Venus's water to evaporate. Once the water was gone, the chemical reactions in the atmosphere, coupled with the intense heat and volcanic activity, led to the release of enormous quantities of carbon dioxide. Carbon dioxide is an even more powerful greenhouse gas than water vapor. Venus's atmosphere today is composed of about 96.5% carbon dioxide, with the remaining 3.5% being primarily nitrogen. This dense blanket of carbon dioxide traps heat with extreme efficiency, creating a surface temperature that averages around 462 degrees Celsius, 864 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure at the surface is also immense, about 92 times that of Earth's at sea level, equivalent to the pressure found nearly a kilometer deep in Earth's ocean. This extreme pressure, combined with the searing heat and corrosive clouds, paints a picture of a truly alien world. The implications of Venus's fate are profound. It demonstrates that a planet's proximity to its star, while a significant factor, is not the sole determinant of its habitability. The composition and behavior of its atmosphere play an equally, if not more, critical role. For Earth, the development of life and geological processes have acted as a thermostat, keeping our planet within a habitable temperature range. The stark contrast between Earth and Venus serves as a powerful lesson in atmospheric science and the delicate equilibrium that allows life to flourish. It highlights how subtle differences in planetary evolution can lead to vastly divergent outcomes, transforming a potentially life-bearing world into a desolate, superheated inferno. Our understanding of Venus's fiery embrace helps us appreciate the unique circumstances that make Earth so special, and underscores the importance of safeguarding our own planet's atmosphere. And so, The fiery embrace of Venus reminds us that even in the vastness of creation, the most profound lessons are often found in the starkest contrasts, urging us to cherish the gentle warmth that cradles our own existence. Mercury's swift dance, a close encounter with the Sun. Mercury, the smallest planet in our solar system and the closest to the Sun, presents a fascinating paradox in planetary formation. Its existence so near the Sun, a region of intense radiation and gravitational forces, raises questions about how such a dense, rocky world could have coalesced from the primordial solar nebula. Unlike the gas giants that formed further out where ice could condense and accrete vast amounts of hydrogen and helium, Mercury's formation is thought to have occurred under conditions that would seemingly hinder the growth of large bodies. The prevailing theory suggests that Mercury may have once been a much larger planet, perhaps similar in size to Earth, with a substantial mantle and a significant amount of volatile elements. However, the intense heat from the young Sun, coupled with frequent, powerful impacts from planetesimals and protoplanets during the chaotic early stages of solar system evolution, is believed to have stripped away much of its outer layers. Imagine the early Sun, a furious inferno, bombarding its nascent planetary system with relentless energy. For Mercury, this proximity meant that any lighter, more volatile materials, the elements that would form a substantial atmosphere or a deep mantle, were vaporized and pushed outward by the solar wind and thermal radiation. This process, sometimes referred to as thermal evaporation or solar wind stripping, would have preferentially removed the less dense components, leaving behind a disproportionately large, dense metallic core. This core, primarily composed of iron and nickel, makes up an astonishingly high percentage of Mercury's total mass, estimated to be around 85%. To put this into perspective, Earth's core constitutes only about 30% of its mass. This extreme density is a key characteristic that distinguishes Mercury from its terrestrial siblings. The very act of formation in such a hostile environment might have involved a series of violent collisions. One compelling hypothesis posits that Mercury formed from the debris of a larger protoplanet that was itself shattered by an impact. In this scenario, a protoplanet of considerable size, perhaps with a composition similar to other terrestrial planets, experienced a catastrophic collision with another large body. The energy of this impact would have vaporized and ejected a significant portion of its rocky mantle, leaving behind the denser, metallic core. This core then continued to accrete the remaining debris, forming the Mercury we observe today. Another contributing factor to Mercury's peculiar composition might be its orbital dynamics. Its highly elliptical orbit means that its distance from the Sun varies considerably, exposing it to fluctuating levels of solar radiation and gravitational stress. This dynamic environment could have played a role in its evolutionary path. The gravitational influence of the Sun is immense, and in Mercury's case, this proximity means it orbits the Sun in a mere 88 Earth days, making it the fastest-moving planet. This rapid transit, this swift dance, is a constant reminder of its intimate relationship with our star. The solar wind, a stream of charged particles emanating from the Sun, also plays a crucial role. While it's thought to have stripped away Mercury's original mantle, it also contributes to the planet's tenuous exosphere, a very thin layer of atoms and molecules that is constantly being replenished. The intense solar radiation also leads to extreme temperature variations on Mercury's surface, with daytime temperatures soaring to over 400 degrees Celsius and plummeting to below -170 degrees Celsius at night. This stark contrast is a testament to the planet's lack of a substantial atmosphere to regulate temperature and its direct exposure to the Sun's fury. Understanding Mercury's formation is not just about cataloging planetary characteristics. It offers profound insights into the diverse processes that can shape worlds within a single solar system. It demonstrates that the conditions for planetary growth are not uniform, and that even in the most extreme environments, celestial bodies can emerge, albeit in forms that defy simple expectations. Mercury, in its dense, iron-rich composition and its rapid, sun-kissed orbit, stands as a unique testament to the dynamic and often violent history of our cosmic neighborhood. In the sun's fierce embrace, a dense heart beats, a swift dance of iron and rock, a testament to resilience forged in cosmic fire. The gas giant's magnetic shield, protecting the inner system. Imagine, if you will, a vast, invisible ocean of energy surrounding our sun. This is the solar wind, a constant stream of charged particles, mostly protons and electrons, ejected from the sun's upper atmosphere, its corona. For billions of years, this relentless flow has swept outwards, shaping planets and influencing the very fabric of our solar system. But this cosmic gale is not an unhindered force. It encounters formidable barriers, and among the most powerful are the magnetic fields generated by our gas giants: Jupiter, Saturn, Uranus, and Neptune. These colossal planets, vastly different from our rocky inner world, possess magnetic fields of immense strength, far exceeding that of Earth. Jupiter's magnetosphere, for instance, is the largest and most powerful in the solar system, extending millions of kilometers into space, so vast it would engulf the sun if viewed from Earth. These magnetic fields act like invisible shields, deflecting and trapping a significant portion of the solar wind. The charged particles are guided by the magnetic field lines, forming complex structures like the magnetopause, where the solar wind's pressure is balanced by the planet's magnetic field, and the magnetotail, a long, comet-like stream of plasma pulled out by the solar wind. Within these magnetospheres, trapped particles can create spectacular auroras, similar to Earth's but on a grander scale, painting the skies of these distant worlds with ethereal light. But their protective role extends far beyond these beautiful displays. By deflecting the harsh solar wind, these magnetic shields have played a crucial, albeit often overlooked, role in safeguarding the development and habitability of the inner solar system, including our own planet Earth. Without these colossal guardians, the constant bombardment of charged particles could have stripped away Earth's atmosphere over eons, rendering it a barren, lifeless rock, much like Mars appears to be. The solar wind, while a source of energy and dynamic phenomena, can also be destructive. It can erode planetary atmospheres, damage delicate organic molecules, and increase radiation levels. The gas giants, through their powerful magnetic fields, act as cosmic sentinels, absorbing much of this energetic onslaught. They effectively create a protective bubble, a region of relative calm within the turbulent solar system. The strength of a gas giant's magnetic field is intrinsically linked to its internal structure and dynamics. Jupiter's field, for example, is generated by the rapid rotation of its metallic hydrogen core, a state of matter achieved under immense pressure. Saturn's field is also attributed to metallic hydrogen, though its structure is remarkably symmetrical. Uranus and Neptune, the ice giants, have more complex and offset magnetic fields, likely generated in a layer of conductive icy fluids. The interaction between the solar wind and these magnetospheres is a continuous dance, a dynamic equilibrium that has persisted for billions of years. During periods of increased solar activity, like solar flares or coronal mass ejections, the solar wind intensifies. This can lead to more pronounced interactions with the magnetospheres, causing them to compress and then rebound, releasing stored energy in spectacular auroral displays and sometimes even influencing the ionospheres of inner planets. The discovery and study of these magnetospheres have been a cornerstone of planetary science, revealing the intricate workings of our solar system and the profound interconnectedness of its celestial bodies. They remind us that even in the vastness of space, there are forces at play that shape destinies, and that the seemingly empty void is, in fact, alive with energetic currents and protective fields. The gas giants, in their immense silent grandeur, are not just distant orbs. They are active participants in the ongoing story of our solar system, their magnetic shields a testament to the complex, dynamic, and often protective nature of cosmic phenomena. They are the silent guardians, the unseen protectors, whose influence has allowed the delicate tapestry of life to unfurl on our pale blue dot. The colossal embrace of their magnetic fields, a silent, powerful testament to cosmic protection, has allowed the fragile seeds of life to find fertile ground. Saturn's rings, a symphony of ice and rock. The magnificent rings of Saturn, a celestial spectacle that has captivated observers for centuries, are not solid structures, but rather a vast, intricate collection of countless individual particles, ranging in size from microscopic dust grains to colossal boulders, each independently orbiting the gas giant. These particles are overwhelmingly composed of water ice, accounting for over 99% of their mass, with trace amounts of rocky material and organic compounds lending subtle variations in color and composition. The sheer scale of this icy debris field is breathtaking. The main rings stretch outwards for hundreds of thousands of kilometers, yet in most places, they are astonishingly thin, often no more than a few tens of meters thick. This delicate architecture, a cosmic ballet of frozen water, is a testament to the dynamic processes that shaped our solar system. The origin of these rings remains a subject of ongoing scientific inquiry, with the leading theories suggesting they are either the shattered remnants of a moon or comet that strayed too close to Saturn's gravitational embrace, or perhaps they are material that never coalesced into a moon during the planet's formation. Regardless of their precise genesis, the rings are remarkably dynamic. Gravitational interactions with Saturn's numerous moons play a crucial role in shaping their structure. Tiny shepherd moons, for instance, carve out clear gaps within the rings, most notably the Cassini division, while other moons exert tidal forces that create intricate waves and ripples. The constant bombardment of micrometeoroids and ultraviolet radiation from the Sun also contributes to the slow erosion and evolution of the ring particles, a continuous process of cosmic recycling. The reflectivity of the ice particles, particularly the larger ones, is what gives Saturn's rings their brilliant, ethereal glow, a stark contrast against the dark expanse of space. The subtle variations in hue, from brilliant white to a faint reddish brown, are attributed to the presence of impurities, such as iron oxides or carbonaceous material, embedded within the ice. These impurities can also influence the way sunlight scatters, further enhancing the visual complexity of the rings. Spectroscopic analysis has revealed the presence of complex organic molecules, such as tholins, on the surface of some ring particles, hinting at the chemical processes occurring in this frigid environment. The rings are not static. They are constantly being replenished by material shed from Saturn's inner moons and potentially by cometary impacts. This continuous influx of fresh ice helps to maintain the ring's brilliance and extent. The sheer density of particles in some regions, particularly within the main A and B rings, is so high that they appear as solid bands from a distance. Yet at a closer vantage point, the vastness of space between each icy fragment becomes apparent. The gravitational influence of Saturn itself is the primary force holding these particles in orbit, preventing them from dispersing into space. The planet's immense mass creates a gravitational field that effectively tethers the ring system, allowing it to persist for billions of years, though its ultimate fate is still a subject of scientific debate. Some models predict that the rings will eventually dissipate, either by spiraling into Saturn or by being ejected into interplanetary space. However, for now, they remain a breathtakingly beautiful and enduring feature of our solar system. The intricate patterns and divisions within the rings are not random. They are the result of complex gravitational resonances between the ring particles and Saturn's moons, creating a celestial clockwork of orbital mechanics. The spokes, transient phenomena that appear as dark streaks across the rings, are thought to be caused by charged dust particles levitating above the ring plane, influenced by Saturn's powerful magnetic field. The sheer volume of ice present in Saturn's rings is staggering, estimated to be enough to fill a small moon. This vast reservoir of frozen water represents a significant fraction of the total water in the inner solar system, a poignant reminder of the cosmic origins of even the most familiar elements. The delicate balance of forces, from the sun's radiation to the gravitational tugs of moons, creates a constantly evolving masterpiece, a testament to the dynamic nature of the cosmos. The light that reaches us from Saturn's rings has traveled across unimaginable distances, carrying with it the echoes of their creation and the subtle whispers of ongoing cosmic change. In the silent dance of ice and gravity, we witness a frozen echo of creation, a reminder that even the most distant celestial wonders are woven from the same cosmic dust that forms our very being. Uranus's tilted orbit, an ancient cataclysm asterisk. Our journey through the formation of our solar system brings us to a truly peculiar member, Uranus. While most of the planets orbit the Sun in a relatively upright manner, Uranus spins on its side, with its axis tilted at an astonishing 98 degrees. This isn't a gentle lean. It's as if the planet was knocked over in a cosmic wrestling match. To understand this, we must delve into the chaotic early days of our solar system, a period characterized by frequent, immense collisions. Imagine a swirling disk of gas and dust, populated by countless nascent planets or planetesimals, all jostling for space and mass. In this dynamic environment, catastrophic events were not the exception, but a common part of the process. The prevailing scientific hypothesis suggests that Uranus's extreme tilt is the result of a colossal impact with an object at least as large as Earth, possibly twice its mass. This hypothetical impactor, sometimes referred to as Theia, though this name is more commonly associated with the impact that formed our moon, would have struck Uranus with unimaginable force. The sheer energy released by such a collision would have been immense, capable of not only altering the planet's spin, but also ejecting a significant portion of its early atmosphere and mantle into space. This debris would then have coalesced, forming the system of rings and moons that we observe around Uranus today. The impact would have reshaped the planet's internal structure, potentially leading to its unique composition, which is rich in ices like water, ammonia, and methane, hence its classification as an ice giant. The orientation of this impact is crucial. If it struck from the side, it would have effectively spun Uranus onto its side, explaining its peculiar axial tilt. This single, cataclysmic event would have fundamentally changed the planet's trajectory and its relationship with the Sun. For billions of years, Uranus has orbited the Sun on its side, leading to extreme seasons. For a quarter of its orbit, one pole faces the Sun, experiencing continuous daylight, while the other pole is plunged into perpetual darkness. Then, as the planet continues its slow, 84-year journey around the Sun, the situation reverses. This prolonged exposure to sunlight on one pole, followed by prolonged darkness, creates a seasonal cycle unlike any other in our solar system. The atmosphere of Uranus, being so different from its gas giant neighbors Jupiter and Saturn, also hints at this violent past. While Jupiter and Saturn are primarily composed of hydrogen and helium, Uranus and Neptune have a higher proportion of heavier elements, including those ices. This suggests that they formed further out in the solar nebula, where temperatures were colder, and these heavier, volatile compounds could condense. However, the massive impact likely stripped away much of the lighter gases that might have been present, leaving behind a denser, icier core. The very moons of Uranus also tell a story of this violent origin. Many of them orbit in Uranus's equatorial plane, which is now aligned with its tilted rotation. This reinforces the idea that they formed from the debris disk created by the impact, or were captured by the planet after it was already in its tilted orientation. The discovery of Uranus itself in 1781 by William Herschel was already a significant moment, expanding our known solar system. But understanding its tilted spin has revealed a deeper, more dramatic narrative of its birth. It's a testament to the raw, untamed forces that shaped our celestial neighborhood. The energy involved in such an impact is almost incomprehensible, a cosmic violence that ultimately led to the unique world we see today. This ancient cataclysm, though devastating, was also a generative force, contributing to the diverse and fascinating collection of worlds that populate our solar system. The story of Uranus's tilt is a powerful reminder that the cosmos is not always a serene and orderly place. It is a realm of immense power, dramatic events, and profound transformation. The very fact that Uranus spins on its side is a whisper from a time when our solar system was still finding its footing, a time of fierce cosmic ballet and world-altering collisions. It is a testament to the resilience of planetary formation, that even after such a violent event, a planet could continue to exist, to orbit, and to evolve. The enduring mystery of this tilt serves as a constant reminder of the dynamic and often violent processes that govern the universe, and how even the most stable-seeming celestial bodies carry the scars of their tumultuous beginnings. This tilted orientation, a direct consequence of a cosmic collision, has sculpted its atmosphere, its seasons, and the very orbits of its moons, painting a vivid picture of a solar system born from chaos and gradual, yet sometimes explosive, organization. The sheer scale of the energy required to tip a planet of Uranus's size speaks volumes about the forces at play during the solar system's infancy. It is a narrative written in the very fabric of the planet, a story of impact, upheaval, and eventual, albeit peculiar, stability. The study of Uranus's tilt continues to inform our understanding of planetary formation and evolution, offering crucial insights into the potential diversity of planetary systems throughout the galaxy. It's a stark, yet beautiful, illustration of how even catastrophic events can contribute to the rich tapestry of cosmic existence. This icy giant, spinning on its side, is a living monument to the violent, awe-inspiring genesis of our solar system, a constant reminder of the grand, energetic forces that sculpted our cosmic home. The scientific quest to understand this phenomenon is a testament to our enduring curiosity about our place in the universe and the incredible journeys our planets have taken to reach their present state. Each of its moons, each of its rings, and indeed, its very orientation, are pieces of a puzzle that, when assembled, tell a story of incredible cosmic drama. The planet's unusual tilt is not just a scientific curiosity. It's a profound clue to the turbulent and transformative history of our solar system, a history etched in the very celestial bodies that surround us. This celestial anomaly, this profound tilt, serves as a constant, silent reminder of the raw power and unpredictable nature of cosmic evolution, a narrative of creation that often unfolds through immense, planet-altering events. The planet's sideways spin is a stark, yet beautiful reminder of the chaotic, dynamic processes that shaped our solar system, a testament to the fact that even in the vastness of space, cataclysm can be a precursor to unique and enduring existence. The scientific exploration of Uranus's tilt offers a profound perspective on the forces that shaped our home, a narrative of cosmic violence that ultimately led to the serene, albeit tilted, orbit we observe today, a celestial body forever marked by its cataclysmic past. The sheer scale of the impact required to achieve such a tilt is almost unfathomable, a testament to the volatile nature of planetary formation in the early solar system, a period where collisions were not just possible, but probable, shaping the planets in ways we are still beginning to comprehend. This tilted spin is a direct imprint of that ancient violence, a visible scar from a cosmic event that fundamentally altered the planet's destiny and its place within our solar system, a story of creation written in the very orientation of a world. It is a reminder that the universe is not static, but a place of constant change, where even the most profound transformations can arise from moments of immense, planet-shaping power, leaving behind worlds with unique characteristics and stories to tell. The ongoing study of Uranus and its peculiar tilt continues to unlock secrets of planetary evolution, providing invaluable data for understanding the formation of other planetary systems and the potential for life beyond our own world, all stemming from a single, monumental impact. This unique characteristic serves as a powerful reminder of the diverse and often violent processes that govern the cosmos, and how these events, though destructive, can also be the architects of unique and enduring celestial bodies, contributing to the grand, unfolding narrative of the universe. The sideways spin of Uranus, a direct consequence of a monumental impact, is a constant, silent witness to the energetic and often chaotic genesis of our solar system, a narrative of creation that is as awe-inspiring as it is profound. This ancient cataclysm, a moment of immense cosmic violence, is forever etched into the very being of Uranus, shaping its orbit, its seasons, and the very character of this distant, enigmatic world, a profound testament to the transformative power of cosmic events. The planet's unusual axial tilt, a direct result of a monumental collision, offers a unique window into the turbulent and dynamic processes that govern the formation of our solar system, a powerful reminder that creation often arises from destruction, and that even the most violent events can contribute to the richness and diversity of the cosmos. The universe, in its grand design, often writes its most profound stories not in gentle whispers, but in the thunderous echoes of cataclysm, a truth beautifully embodied by the sideways spin of Uranus, a planet forever dancing to the rhythm of an ancient, world-altering impact. Neptune's distant reign, a world of winds. Far out in the dim twilight of our solar system lies Neptune, a world of profound distance and breathtaking atmospheric dynamics. It is the eighth and farthest known planet from our Sun, a majestic blue giant that whispers tales of cosmic forces and the sheer, unbridled power of nature. Neptune's reign is one of winds, of storms that dwarf anything we experience on Earth, a testament to the immense energies at play in the outer reaches of our stellar neighborhood. Unlike the rocky inner planets, Neptune, along with its neighbor Uranus, belongs to the class of ice giants. This means its composition is vastly different, dominated by heavier elements like water, ammonia, and methane, layered above a rocky core. These volatile compounds, under immense pressure and frigid temperatures, behave in ways that are still a source of deep scientific inquiry. The most striking characteristic of Neptune is its incredibly dynamic atmosphere. It is home to the fastest winds in the solar system, reaching speeds of over 1,200 miles per hour, or about 2,000 kilometers per hour. To put that into perspective, that's faster than the speed of sound on Earth. These winds are not just fleeting gusts. They are sustained, powerful currents that sculpt the planet's appearance, driving vast cloud formations and generating immense storms. The iconic Great Dark Spot, observed by the Voyager 2 spacecraft in 1989, was a colossal storm system, roughly the size of Earth, that raged for years before eventually dissipating. Its presence highlighted the turbulent nature of Neptune's atmosphere, a stark contrast to the seemingly serene blue hue of the planet. The blue color itself is a result of methane in Neptune's atmosphere. Methane absorbs red light and reflects blue light, giving the planet its distinctive sapphire appearance. However, the sheer intensity of the winds and the swirling cloud patterns suggest that there are other, less understood atmospheric processes at play. Scientists believe that Neptune's internal heat source plays a significant role in driving these extreme weather systems. While the Sun's energy is significantly diminished at Neptune's distance, the planet radiates more heat into space than it receives from the Sun. This internal warmth, likely a remnant of its formation, fuels the powerful convection currents that churn its atmosphere. The cloud tops of Neptune are composed of ammonia ice crystals, water ice, and possibly methane ice. These clouds are constantly being churned and reformed by the relentless winds. The planet's extreme axial tilt, similar to Uranus, also contributes to its unique climate. Neptune is tilted at an angle of about 28 degrees, leading to pronounced seasonal variations, though these seasons last for decades due to its long orbital period of 165 Earth years. Imagine a single season lasting for over 40 Earth years. It's a timescale that stretches our terrestrial understanding of weather. The immense gravitational pull of Neptune also influences its moons. Triton, its largest moon, orbits Neptune in a retrograde direction, meaning it orbits in the opposite direction to the planet's rotation. This is a highly unusual characteristic for a large moon, and suggests that Triton may have been a captured object from the Kuiper Belt, a region of icy bodies beyond Neptune. The gravitational interplay between Neptune and Triton is thought to be responsible for some of Neptune's atmospheric dynamics, creating tidal forces that further stir its gaseous envelope. The study of Neptune continues to push the boundaries of our understanding of planetary science. Its extreme winds, its internal heat, and its unusual atmospheric composition offer valuable insights into the formation and evolution of gas and ice giants. It serves as a cosmic laboratory, allowing us to explore the fundamental principles of fluid dynamics and atmospheric physics under conditions far removed from our own. The sheer scale of Neptune's weather systems reminds us of the vastness and complexity of the universe, and how much more there is yet to discover. Neptune's distant reign reminds us that even in the quietest corners of our solar system, immense power and ceaseless motion are at play, a cosmic ballet of energy and atmosphere shaping worlds far beyond our immediate grasp. The solar wind's influence, shaping the cosmic landscape. Imagine, if you will, a constant, invisible river flowing outwards from the heart of our sun. This is the solar wind, a stream of charged particles, primarily electrons and protons, that emanates from the sun's upper atmosphere, the corona. It's not truly a wind in the terrestrial sense, for it's not made of air, but rather a plasma, a superheated, electrically charged gas. This ceaseless outflow, traveling at incredible speeds, often exceeding hundreds of kilometers per second, plays a profound and often underestimated role in shaping the very fabric of our solar system, influencing planets, moons, and even the vast interstellar medium that lies beyond. The corona, the Sun's outermost atmosphere, is a place of extreme heat, reaching millions of degrees Celsius. At these temperatures, the particles are so energetic that they overcome the Sun's gravitational pull and escape into space. This continuous expulsion forms the solar wind. It's a fundamental process that has been ongoing for billions of years, a silent sculptor of the cosmic environment around us. The influence of this solar wind is felt most dramatically by the planets. For those planets possessing their own magnetic fields like Earth, Jupiter, and Saturn, the solar wind encounters a powerful shield. These magnetic fields, generated by the motion of molten metal within the planet's cores, create a protective bubble known as the magnetosphere. The solar wind particles are deflected around this magnetosphere, their paths bent and redirected. This deflection is not perfect. Some particles inevitably leak in, particularly at the poles, where the magnetic field lines converge. These inflowing particles are responsible for one of nature's most breathtaking displays, the aurora borealis and aurora australis, the dancing lights of the polar skies. They collide with atoms and molecules in our upper atmosphere, exciting them and causing them to emit light. Without these magnetic shields, the solar wind would bombard planetary surfaces, stripping away atmospheres and rendering them barren and inhospitable. Consider Earth, our magnetosphere, a testament to the dynamic dynamo within our planet, is our primary defense against the relentless onslaught of the solar wind. It protects our atmosphere from being gradually eroded over eons, a fate that may have befallen planets like Mars. The solar wind, though invisible, is a force of immense power, a constant pressure that sculpts our planet's interaction with the wider cosmos. The gas giants, with their colossal magnetic fields, possess magnetospheres that dwarf even Earth's. Jupiter's magnetosphere is so vast that it extends for millions of kilometers, encompassing its innermost moons. The intense magnetic fields of these giants trap vast quantities of charged particles from the solar wind, creating regions of intense radiation. These environments are incredibly hostile to life as we know it, yet they are also sites of fascinating physical phenomena, including powerful radio emissions. Even planets without significant magnetic fields like Venus and Mars are profoundly affected. The solar wind directly interacts with their upper atmospheres, a process called atmospheric stripping. Over billions of years, this constant bombardment can erode away a planet's atmosphere, leading to a drier, colder, and less habitable world. The thinner atmosphere of Mars, for instance, is believed to be a consequence of its weak magnetic field and its prolonged exposure to the solar wind. This process is a stark reminder of how delicate planetary atmospheres can be and how crucial a protective magnetic field is for retaining them. The solar wind also plays a vital role in shaping the heliosphere, the vast bubble of space dominated by the Sun and its magnetic field. The heliosphere extends far beyond the orbit of Pluto, acting as a protective barrier against the high-energy cosmic rays originating from outside our solar system. The solar wind pushes against this interstellar medium, creating a boundary known as the heliopause, where the pressure of the solar wind is balanced by the pressure of the interstellar medium. This boundary is a crucial frontier, defining the extent of our Sun's influence in the galaxy. The heliosphere is not static. It expands and contracts with the Sun's 11-year cycle of activity. During periods of high solar activity, the Sun releases more energetic particles and stronger magnetic fields, causing the heliosphere to expand. Conversely, During periods of low solar activity, it contracts. This dynamic interplay between the sun's output and the interstellar medium is a continuous process of cosmic sculpting. Furthermore, the solar wind carries with it the sun's magnetic field, embedded within the plasma. This interplanetary magnetic field, also known as the heliospheric magnetic field, extends throughout the solar system, influencing the paths of charged particles and the dynamics of planetary magnetospheres. It's a complex, swirling structure that plays a critical role in space weather, the conditions in space that can affect technological systems on Earth and in orbit. The solar wind is not just a passive outflow, it's an active participant in the evolution of our solar system. It has influenced the development of planetary atmospheres, shaped the surfaces of moons and planets through erosion and radiation, and continues to define the boundaries of our solar system's influence. It is a constant, invisible force, a testament to the dynamic and energetic nature of our star, and a fundamental element in the grand cosmic ballet. The solar wind, a silent breath from our star, shapes the cosmic landscape with an invisible hand. The sun's life cycle, a star in its prime. Our sun, a magnificent yellow dwarf star, is currently in the most stable and longest phase of its life, the main sequence. This is a period of equilibrium, a delicate dance between the immense gravitational force pulling inward and the outward pressure generated by nuclear fusion in its core. Imagine a cosmic furnace, tirelessly converting hydrogen into helium, releasing an astonishing amount of energy that travels across 93 million miles to warm our planet. This process, known as nuclear fusion, is the engine of stars. Deep within the sun's core, under pressures and temperatures so extreme they are almost incomprehensible, hydrogen nuclei collide and merge, forming helium. This fusion releases photons, the particles of light, which then embark on a long and arduous journey outward. These photons can take hundreds of thousands of years to reach the sun's surface, bouncing and scattering through the dense plasma of the radiative zone, then churning their way up through the convective zone, before finally bursting forth as sunlight. The sun has been in this main sequence phase for approximately 4.6 billion years, and it is estimated to continue for another 5 billion years. This stability is what allows for the existence of life on Earth. Without this consistent energy output, our planet would be a frozen, desolate world. The sun's mass dictates its lifespan and its eventual fate. More massive stars burn hotter and faster, living much shorter, more dramatic lives, often ending in spectacular supernova explosions. Less massive stars, the red dwarfs, burn far more slowly, potentially lasting trillions of years. Our sun, being of moderate mass, occupies a comfortable middle ground, providing a stable environment for its planetary system for an extended period. The sun's surface, while appearing smooth from afar, is a dynamic and turbulent place. We observe phenomena like sunspots, which are cooler, darker regions caused by intense magnetic activity. These magnetic fields can also erupt, releasing massive bursts of energy and charged particles into space, known as solar flares and coronal mass ejections. These events, while often beautiful to observe through specialized telescopes, can have significant impacts on Earth, affecting satellite communications and power grids. Understanding the sun's life cycle is not just an academic pursuit. It is fundamental to understanding our own existence and our place in the cosmos. It is a reminder that even the most constant and seemingly unchanging celestial bodies are part of a grand, dynamic, and evolving universe. The sun's prime is our present, a gift of warmth and light that has nurtured life for eons. The sun's steady heartbeats for us, a celestial promise of warmth, a golden anchor in the vast, dark sea of existence. The search for exoplanets, echoes of our own formation. Our understanding of how our own solar system came to be is deeply enriched by the ongoing, breathtaking endeavor of searching for planets beyond our sun. These distant worlds, known as exoplanets, are not merely astronomical curiosities. They are profound echoes of our own cosmic genesis, offering us a unique mirror to contemplate our origins. For centuries, humanity gazed at the stars, wondering if other suns harbored other worlds, perhaps even other life. Now, through ingenious scientific methods, we are no longer just wondering, we are discovering. The very techniques we use to find these faraway planets often rely on principles that were at play during our solar system's formation. For instance, the transit method, one of the most successful ways to detect exoplanets, involves observing the slight dimming of a star as a planet passes in front of it. This is akin to imagining a tiny speck of dust, a planetesimal, momentarily obscuring the light of our nascent sun billions of years ago. The radial velocity method, another key technique, detects the wobble of a star caused by the gravitational tug of an orbiting planet. This wobble is a direct consequence of the gravitational dance that occurred as our own planets coalesced from the swirling disk of gas and dust around the young sun. The sheer variety of exoplanets discovered, hot Jupiters orbiting incredibly close to their stars, super-Earths larger than our own planet but smaller than Neptune, and rocky worlds within the habitable zones of their stars, paints a vivid picture of the diverse outcomes of planetary formation. Some of these systems bear striking resemblances to our own, with rocky inner planets and gaseous giants further out, suggesting that the fundamental processes we believe shaped our solar system are indeed universal. Others, however, present entirely new configurations, challenging our existing models and pushing the boundaries of our theoretical understanding. The Kepler Space Telescope, for example, revolutionized exoplanet detection, revealing that planets are not rare anomalies but are, in fact, incredibly common. It is estimated that there are more planets than stars in our galaxy, a staggering thought that underscores the potential for cosmic diversity. The study of exoplanetary atmospheres, now becoming increasingly sophisticated, allows us to probe their composition, searching for biosignatures, the chemical fingerprints that might indicate the presence of life. This quest, while focused on distant worlds, inevitably brings us back to our own planet, to the conditions that allowed life to arise and flourish here. Are there other Earths out there? Worlds where the delicate balance of chemistry, geology, and atmosphere has converged to foster life. The search for exoplanets, therefore, is not just about finding other worlds. It is about understanding the fundamental processes of planet formation, the prevalence of habitable conditions in the cosmos, and ultimately, our own place within this vast and intricate universe. Each newly discovered exoplanet, each subtle wobble of a distant star, each dip in starlight, is a whisper from the cosmic past, a confirmation that the grand, turbulent, and ultimately beautiful process that birthed our solar system is a story being told, again and again, across the immensity of space. The data pouring in from missions like TESS and the James Webb Space Telescope continues to refine our models, allowing us to better understand the factors that lead to the formation of planetary systems like our own, and perhaps even to the emergence of life itself. We are learning that the specific conditions that allowed for the formation of our sun and planets, the precise timing of events, the composition of the primordial nebula, and the gravitational interactions that followed, all contributed to the unique architecture of our solar system. By studying other systems, we can identify which of these factors are essential and which are merely incidental, helping us to understand the likelihood of similar planetary nurseries giving rise to worlds like ours. The discovery of planetary systems with different architectures, such as those with gas giants closer to their stars than the rocky planets, or systems with multiple super-Earths, prompts us to reevaluate our assumptions about the inevitability of our own solar system's configuration. It suggests that while the fundamental laws of physics are universal, the specific outcomes of planet formation can be remarkably diverse, influenced by a complex interplay of initial conditions and subsequent evolutionary processes. This diversity is not a cause for despair, but rather a source of wonder, highlighting the incredible creativity of the cosmos. The ongoing search for exoplanets is a testament to human curiosity and our innate drive to understand our origins. It is a scientific quest that fuels our imagination, expands our perspective, and reminds us that we are part of a much larger, far more astonishing cosmic narrative. Each exoplanet found is a data point, a piece of a grand cosmic puzzle, helping us to reconstruct the story of how worlds, and perhaps life, come to be. In the vast theater of the cosmos, the search for exoplanets illuminates the universal song of creation, reminding us that the dust within us echoes the nebulae from which all stars and worlds are born. The uniqueness of our solar system, a delicate balance. Our solar system, as we observe it today, is a remarkably intricate and, in many ways, unique arrangement of celestial bodies. While the discovery of thousands of exoplanetary systems has shown us that planetary formation is a common cosmic process, the specific configuration and characteristics of our own solar system suggest a level of fine-tuning that has allowed for the emergence and sustenance of life as we know it. This delicate balance isn't accidental. It's the result of a complex interplay of gravitational forces, historical events, and the fundamental laws of physics. Consider, for instance, the arrangement of our planets. We have a series of small, rocky planets in the inner solar system, followed by a vast expanse of space, and then the gas and ice giants in the outer reaches. This separation is largely due to the frost line we discussed earlier, where volatile compounds could condense into solid ice beyond a certain distance from the young sun. This separation is crucial. If the gas giants were closer to the sun, their immense gravity could have disrupted the formation of the inner terrestrial planets, perhaps even flinging them out of the solar system entirely, or causing them to collide. The current arrangement allowed for the formation of stable, rocky worlds like Earth, with just enough mass to retain an atmosphere and a molten core, essential for a protective magnetic field. The presence and influence of Jupiter are particularly noteworthy. Its massive gravitational pull acts as a cosmic vacuum cleaner, deflecting or capturing many comets and asteroids that might otherwise have bombarded the inner planets, including Earth, with devastating regularity. While Jupiter has undoubtedly caused impacts throughout history, its overall effect, according to many scientific models, has been to moderate the frequency of catastrophic collisions in the inner solar system, providing a more stable environment for life to evolve. This is a prime example of a gravitational shepherd, whose very presence, though seemingly immense and potentially disruptive, contributes to a greater stability for the smaller worlds. Furthermore, the orbits of our planets are remarkably stable and nearly circular, especially those of the inner planets. This stability is not guaranteed in planetary systems. Many exoplanet systems exhibit highly eccentric orbits, where planets swing in elongated ellipses, experiencing extreme temperature fluctuations and gravitational perturbations. Such chaotic orbits would make it exceedingly difficult for liquid water to persist on a planet's surface, a cornerstone for life as we understand it. The relative orderliness of our solar system, though not perfectly circular for all bodies, has provided a consistent and predictable environment for billions of years. The existence of our moon is another factor contributing to this delicate balance. The moon's large size relative to Earth has a stabilizing effect on our planet's axial tilt. Without the moon, Earth's tilt would likely wobble much more erratically over geological timescales, leading to extreme and unpredictable climate variations that could have hindered the development of complex life. The moon's gravitational pull also drives our tides, which played a significant role in the early evolution of life by creating tidal pools where simple organisms could be concentrated and exposed to new environmental pressures. The sun itself, our star, is also a key component of this balance. It's a G-type main sequence star, a relatively stable and long-lived class of star. Its luminosity has increased gradually over billions of years, but not so rapidly as to boil away Earth's oceans or freeze it solid. The habitable zone, the region around a star where liquid water can exist on a planet's surface, has shifted outwards over time, and Earth has, for the most part, remained within this life-sustaining zone. If our sun were a more massive, hotter star, its lifespan would be much shorter, and its intense radiation might sterilize any nascent life. If it were a smaller, cooler star, the habitable zone would be much closer, potentially leading to tidal locking where one side of the planet perpetually faces the star, resulting in extreme temperature differences. The very composition of our solar system, with the clear division between rocky inner planets and icy outer giants, is also a product of this delicate balance. This division allowed for the formation of a planet like Earth, with the right mix of elements to form a solid crust, a liquid ocean, and a protective atmosphere. The outer planets, in turn, likely delivered significant amounts of water and organic molecules to the inner solar system via comets and asteroids during the early period of heavy bombardment, seeding the nascent Earth with essential ingredients for life. In essence, the uniqueness of our solar system lies not in any single factor, but in the harmonious convergence of many. It's a testament to a specific set of initial conditions and evolutionary pathways that have, against vast cosmic odds, created an environment conducive to complex chemistry and ultimately, life. This understanding doesn't diminish the wonder of the universe. Rather, it enhances it, highlighting the preciousness of our own planetary home within the grand cosmic tapestry. Our existence here is a whisper in the vast silence, a delicate dance orchestrated by cosmic forces, a fragile balance that allows wonder to bloom. The cosmic dust we are made of, a universal connection. For a long time, we looked up at the stars and saw them as distant, unfeeling entities, entirely separate from ourselves. Yet, the profound truth, uncovered through decades of meticulous scientific inquiry, is that we are, in the most literal and beautiful sense, made of stardust. Every atom within your body, from the calcium in your bones to the iron in your blood, was forged in the fiery furnaces of stars that lived and died billions of years ago. This isn't mere poetry, it's the bedrock of our understanding of the universe. Consider the elements heavier than hydrogen and helium. These are the metals in astronomical terms, and they are the building blocks of everything we see and experience. Hydrogen and helium, the lightest and most abundant elements, were created in the Big Bang itself. But all the rest, carbon, oxygen, nitrogen, silicon, iron, gold, and every other element on the periodic table, were synthesized through nuclear fusion within the cores of stars, or during the cataclysmic explosions of supernovae. When a star like our Sun reaches the end of its life, it doesn't simply vanish. It expands into a red giant, and then sheds its outer layers, dispersing these newly created elements into the interstellar medium. More dramatically, when a massive star exhausts its nuclear fuel, it collapses and then explodes as a supernova. This explosion is incredibly powerful, creating even heavier elements and scattering them far and wide across the galaxy. These elements then become part of the vast clouds of gas and dust that drift between the stars, the very nebulae from which new stars and planetary systems are born. Our own solar system, including Earth, formed from such a cloud, enriched by the remnants of countless generations of stars that came before. The carbon atoms that form the backbone of every organic molecule in your body were once part of a star. The oxygen you breathe was exhaled by ancient stellar furnaces. The iron in your blood was smelted in the core of a star that exploded eons ago. This interconnectedness is staggering. It means that the elements that make up your physical being have traveled immense distances through space and time, undergoing incredible transformations. They have been compressed, heated, fused, and dispersed, all to eventually coalesce into the complex, sentient being that you are. This understanding offers a profound sense of perspective. It dissolves the illusion of separation, revealing a deep, fundamental unity between ourselves and the cosmos. We are not just observers of the universe. We are active participants, woven from its very fabric. The atoms in your fingertips have, in some distant past, been part of a red giant star, or perhaps even the core of a supernova. This realization can be incredibly grounding, reminding us of our place within a grand, ongoing cosmic narrative. It imbues the mundane with a sense of the miraculous, turning the simple act of breathing into a connection with the universe's grandest processes. The dust of dead stars, scattered across the vastness of space, eventually found its way into the primordial cloud that birthed our sun and planets, and ultimately you. It's a reminder that even in our most individual moments, we are part of something immeasurably larger and older. The stardust within us is a testament to the universe's relentless cycle of creation and destruction, a cosmic inheritance that connects us to every star, every planet, and every living thing. We are the universe contemplating itself, forged from the remnants of celestial fires, a fleeting, beautiful echo of cosmic creation. The enduring mystery of origins, a philosophical reflection. The grand narrative of our solar system's formation, from the swirling dust of a nebula to the intricate dance of planets, is a story of immense scale and profound beauty. Yet, as we delve into the scientific details, a deeper, more philosophical layer emerges, the enduring mystery of origins itself. Even with our most sophisticated telescopes and theoretical models, we are still probing the very edges of understanding. We can trace the path of gas and dust coalescing, the gravitational ballet that shaped orbits, the fiery impacts that sculpted worlds. We can observe the processes, identify the ingredients, and map the timelines. But the ultimate asterisk why did this particular cloud of gas and dust ignite? Why did it arrange itself in this specific configuration? These questions, while perhaps unanswerable in a purely empirical sense, are not a source of frustration, but rather an invitation to a deeper form of wonder. The universe, in its vastness and complexity, doesn't always offer neat, contained answers. Instead, it presents us with phenomena that inspire contemplation, that push the boundaries of our knowledge, and in doing so, expand our perspective. The fact that we, as conscious beings, can even ponder these questions, that we can look up at the night sky and marvel at the very processes that led to our existence, is itself an extraordinary testament to the intricate unfolding of the cosmos. The journey of scientific discovery, in this context, becomes less about finding definitive endpoints and more about embracing the ongoing process of inquiry, about appreciating the elegance of what we can understand, and finding a quiet peace in the profound mystery of what remains beyond our current grasp. This cosmic origin story, therefore, is not just a scientific account. It's a philosophical prompt, a gentle reminder of our place within an unfolding, awe-inspiring universe, a universe whose deepest secrets continue to beckon us towards quiet contemplation and a profound sense of connection. The very act of questioning our origins connects us to the universe's own grand, unanswerable questions. The ongoing evolution of our solar system, a cosmic continuum. Our solar system, this grand celestial family, is not a static masterpiece, frozen in time at the moment of its formation. Rather, it is a dynamic, ever-changing entity, a cosmic continuum in perpetual motion. The forces that shaped its birth continue to sculpt its present and will undoubtedly dictate its future. Even now, subtle shifts are occurring, driven by the relentless dance of gravity, the steady output of our sun, and the occasional dramatic interlopers from the vast interstellar ocean. Think of the sun itself, the heart of our system. It is a star, and like all stars, it has a lifespan. It is currently in its main sequence phase, a period of relative stability where it fuses hydrogen into helium, a process that has been ongoing for billions of years and will continue for billions more. But this phase is not eternal. Eventually, the sun will exhaust its core hydrogen fuel. It will swell into a red giant, engulfing the inner planets, including our own Earth, in its fiery embrace. This monumental transformation will fundamentally alter the very fabric of our solar system, rendering it unrecognizable to us now. Even before this dramatic end, the sun's output fluctuates. Solar flares, coronal mass ejections, and changes in its magnetic field create what we call space weather. These events influence the atmospheres of planets, affect satellite communications, and can even pose risks to astronauts. These are not just ephemeral phenomena. They are part of the ongoing evolution, a constant interaction between the sun and its planetary companions. Beyond the sun, the planets themselves are not inert spheres. Their orbits, while appearing remarkably stable over human timescales, are in constant, albeit infinitesimal, flux. Gravitational tugs from each other, particularly from the massive gas giants, cause minute variations in their paths. These are not random wobbles but predictable, albeit complex, interactions governed by the laws of celestial mechanics. Over eons, these tiny adjustments can accumulate, leading to significant changes in orbital configurations. We've observed evidence of this in the past, such as the hypothesized grand tack scenario for Jupiter, where its orbit may have shifted inwards and then outwards, significantly influencing the formation and distribution of the inner planets. The moons orbiting these planets are also undergoing their own evolutionary journeys. Tidal forces, generated by the gravitational pull between a moon and its planet, can cause geological activity, heat their interiors, and even drive the formation of subsurface oceans, as seen on moons like Europa and Enceladus. These processes are not merely geological. They are dynamic, ongoing, and part of the continuous reshaping of these celestial bodies. Furthermore, the solar system is not an isolated island. It exists within the Milky Way galaxy, a vast, swirling collection of billions of stars and interstellar gas. Our solar system is not stationary. It orbits the galactic center at an astonishing speed. As it travels, it encounters varying densities of interstellar gas and dust, and occasionally, it may even pass through nebulae or interact with the gravitational influence of passing stars. These encounters, though infrequent on human timescales, are part of the long-term evolutionary narrative of our solar system. The Oort cloud and the Kuiper belt, those vast reservoirs of icy bodies at the solar system's periphery, are not immutable. Gravitational perturbations from passing stars or even giant molecular clouds can send these icy wanderers hurtling into the inner solar system, manifesting as comets. This constant influx of material from the outer reaches is a testament to the system's dynamic nature, a continuous replenishment and reshaping driven by forces beyond its immediate boundaries. The very definition of our solar system's edge is also a fluid concept. The heliosphere, the magnetic bubble created by the sun's solar wind, expands and contracts with the sun's activity and its position within the galaxy. As we venture further out, the boundaries between our solar system and interstellar space become increasingly blurred. The study of meteorites, those visitors from space, provides us with tangible evidence of ongoing processes. These fragments of asteroids and comets are not just relics of the past. They are material that continues to enter our atmosphere, contributing to the cosmic dust that settles on our planet. This dust, though seemingly insignificant, is a constant reminder of the continuous exchange of matter within our solar system and beyond. Even the rings of Saturn, those iconic celestial adornments, are believed to be relatively young and may be continuously replenished by the breakup of small moons or the collision of icy particles. Their existence is a fleeting moment in cosmic history, a testament to ongoing processes of formation and destruction. The search for exoplanets, worlds orbiting other stars, has revealed an astonishing diversity of planetary systems. This comparative study helps us understand that our own solar system's current configuration might be just one outcome among many possibilities, and that the processes we observe here are likely universal, playing out in countless other stellar nurseries across the cosmos. Our understanding of planetary formation itself is constantly evolving, with new discoveries challenging and refining our models. We are witnessing the unfolding story of our solar system not as a finished product, but as a living, breathing entity, a testament to the enduring power of cosmic forces. The grand cosmic ballet continues, a slow, majestic performance of gravity, light, and matter, forever weaving the destiny of our solar system. Our calm exploration has covered the grand, sweeping narrative of our solar system's birth, from the initial, swirling dust and gas of a vast nebula to the intricate dance of planets, moons, and the icy bodies that populate its outer reaches. We have revisited the fiery genesis of our sun, the relentless accretion that built worlds, and the dramatic collisions that sculpted them into the forms we recognize today. We've considered the profound implications of celestial mechanics, the delicate balance that allows for life on our particular planet, and the enduring mysteries that still whisper from the farthest edges of our cosmic home. And in this quiet contemplation, perhaps you can feel a gentle shift within. The vastness we've explored, the immense timescales, the sheer, almost incomprehensible forces at play, they are not meant to overwhelm but to offer a different kind of perspective. You, in this moment, are a part of this grand, unfolding story. The atoms that make up your being were forged in the heart of ancient stars, scattered across the cosmos, and eventually gathered to form this very world, this very solar system. To understand where we came from is to understand our fundamental connection to the universe itself, a connection that can, in its own way, be deeply comforting. It is time to rest now. Allow the echoes of this cosmic cradle to lull you into a deep, peaceful slumber. Let the stardust settle and the quiet wonder of creation carry you away. Sleep well. Good night. If you happen to still be awake, you can drift into the next chapter now, continuing this journey of quiet wonder.